Hello there and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route towards sleep. Tonight we're going to wander toward one of the biggest questions a mind can hold, and thankfully we do not have to hurry there. The universe itself is in no rush. It has already taken billions of years to get from its hot, crowded beginning to this quiet moment in which you and I can sit here, thinking about stars, darkness, time, and whatever may wait beyond the farthest future. Our question tonight is simple to ask and surprisingly difficult to answer. What happens after the end of the universe? Not after the end of a planet or a star or even a galaxy, but after the whole grand cosmic story has spent all its fuel, faded through its final light, and reached whatever comes next, if next is even the right word. It is a strange thing to think about at bedtime, I admit. Most people, when trying to relax, do not usually begin by considering the final condition of all matter and energy. They might choose a cup of tea, a soft blanket, perhaps a book with no urgent plot. And yet there is something oddly calming about looking far enough ahead. The little worries of the day become smaller when placed beside a universe that measures time in stretches so long that even the oldest mountains seem like brief visitors. A missed email, an awkward conversation, a sock that has somehow vanished into the laundry dimension. All of it starts to feel less heavy when we remember that the stars themselves are temporary. Not meaningless, not pointless, just temporary. And temporary things can still be beautiful. In fact, they usually are. Before we drift into that deep future, let me ask you something gentle. Where are you listening from tonight, and what is the sky like where you are? Maybe it is late evening, and the room around you is settling into that familiar hush when the day has finally stopped asking so much of you. Maybe it is raining against the window, or perhaps the air is still, and the city outside is humming quietly, like a machine trying to fall asleep. Maybe it is morning where you are, and you're using this as a soft companion while the world wakes up. Wherever you are, you're sitting on a small spinning planet beneath a universe that is still changing, still expanding, still carrying ancient light across distances so enormous that the numbers begin to feel less like measurements and more like very patient guesses. And if you find this kind of quiet science soothing, or if it gives your thoughts somewhere calm to rest, I would be grateful if you gave the video a like, subscribed, or left a little note about where in the world you're listening from. It helps this small corner of calm reach other curious travellers who might also need a peaceful place to think about impossibly large things without being rushed through them. I do hope tonight's subject does not keep you awake, but if it does, at least you will be awake for a respectable reason. There are worse causes of insomnia than wondering about the ultimate fate of reality. So let us begin gently, not at the end, but with the idea of endings themselves. We're used to endings in ordinary life. A candle burns down, a season changes, a song reaches its last note, a person closes a book and sets it on the bedside table. But the universe is not a candle in any simple sense, and it is not a book with a clear last page. When scientists speak about the end of the universe, they are not usually imagining a sudden curtain dropping, or a cosmic alarm bell ringing, or all the galaxies politely switching off at the same time. The end of the universe, if the most widely accepted picture is correct, is not likely to be dramatic in the way films like to be dramatic. It may not be loud, it may not be bright, it may not even be an event in the usual sense. It may be more like a gradual running down, a slow thinning out, a long fading of possibilities. To understand why, we have to remember that the universe is not standing still. It is expanding. Space itself is stretching, carrying galaxies away from one another across the cosmic ocean. This does not mean that galaxies are flying through space from one central point like sparks from a firework. It means that the distances between very large structures are growing because the fabric of space is changing. On small scales, gravity still holds things together. Earth does not expand away from the sun. Your chair does not expand away from the floor, which is fortunate, because bedtime would become unnecessarily complicated. Galaxies can remain bound. clusters of galaxies can remain bound. But on the larger scales, the universe grows wider and emptier with time. This expansion is one of the key reasons the far future looks so quiet. As space stretches, distant galaxies move farther beyond our reach. Their light becomes weaker and redder as it crosses the growing distances. In the extremely distant future, many galaxies that can be seen today will slip beyond the observable horizon, not because they vanish in their own neighbourhoods, but because their light will no longer be able to reach observers like us, or whatever distant descendants of observers may exist. The night sky of the far future would not look like ours. It would not be crowded with evidence of the wider cosmos. It would be lonelier. A civilization born in that era, if such a thing could exist, might look up and see mostly its own local group of stars, unaware that the universe was once filled with visible galaxies in every direction. Imagine living in a library after most of the books had drifted silently beyond the walls, but long before the universe becomes truly dark, the stars themselves must change. Stars are not permanent lamps, they are engines, and they shine because they are spending fuel. Deep in their cores, under pressure and heat beyond ordinary imagination, they fuse lighter elements into heavier ones and release energy. That energy becomes the light that warms planets, paints nebulae, and gives astronomers something lovely to point telescopes at. Our Sun is one such star, steady enough for life to have developed on Earth, but not eternal. In several billion years, it will change dramatically. It will swell, shed outer layers, and eventually leave behind a dense remnant called a white dwarf. The details matter for Earth, of course, but in the larger story, our Sun is just one member of an enormous population. Across the universe, stars are being born from clouds of gas and dust, shining for millions or billions or even trillions of years depending on their mass, and then moving into old age. The most massive stars live fast and die violently. They burn through their fuel quickly, then collapse and explode as supernovae, scattering heavy elements into space. Those elements help form new stars, new planets, and in at least one case we know of, living creatures who become concerned about the end of everything while lying under blankets. Smaller stars are far more patient. Red dwarf stars, the small, cool stars that are extremely common in the universe, can burn for astonishingly long times. Some may continue shining for trillions of years. Compared with them, our Sun is almost reckless. Yet even red dwarfs have limits. Give them enough time, and they too will exhaust what they can use. Star formation will slow as the raw materials are locked away in stellar remnants, planets, black holes, and diffuse gas that no longer gathers efficiently into bright new suns. This is where the future begins to feel less like a grand fireworks display and more like a household gradually running out of candles. For a long while, there will still be light. Old stars will continue to glow. Stellar remnants will cool. Galaxies will evolve, collide, and settle. But eventually, fewer new stars will form, then almost none. The universe will enter an era where the bright stellar age has passed. The great starry activity that makes our present cosmos so beautiful will become a memory written into faint radiation and cold matter. If there were eyes to see it, those eyes would need patience beyond anything human life has ever required. Still, the end of starlight is not the end of everything. The universe is full of leftovers, and cosmic leftovers are more interesting than the ones in the back of a refrigerator. There will be white dwarfs, neutron stars, black holes, rogue planets, cold dust, and particles drifting through immense darkness. White dwarfs, which are the cooling cores of stars like our Sun, will slowly radiate away their remaining heat. Over vast stretches of time, they're expected to become black dwarfs, cold dark objects no longer shining visibly. None are thought to exist yet, because the universe is not old enough for any white dwarf to have cooled that far. This is a useful reminder that when we speak about the end of the universe, we're speaking about time so far ahead that many predicted objects have not even had time to appear. the future contains kinds of darkness that are still waiting to be made. Neutron stars are another kind of remnant, formed when massive stars collapse into incredibly dense objects. A spoonful of neutron star matter, if it could somehow be brought to Earth without causing many practical problems, would weigh more than mountains. These objects may slowly cool, spin down and change over unimaginable ages. Black holes, meanwhile, may become some of the last major objects in the universe. They're regions where gravity is so strong that not even light can escape once it passes the boundary known as the event horizon. For a long time, black holes may seem like final vaults, places where matter goes and does not return. They can swallow stars, gas, radiation, and other black holes. In the deep future, when stars are gone and galaxies have quieted, black holes may be among the only large structures left with any real drama around them. And yet even black holes may not be forever. According to our best understanding of quantum effects near their horizons, black holes should very slowly lose energy through what is called Hawking radiation. For ordinary black holes, this process is absurdly slow. A black hole with the mass of a star would take far, far longer than the current age of the universe to evaporate. The giant black holes at the centres of galaxies would last even longer. They are not going anywhere soon. If a black hole had a calendar, it would not need to buy a new one very often. But over enough time, even these dark giants may shrink, fade, and finally disappear in a last release of radiation. The universe, once full of stars, may eventually become a thin bath of low-energy particles and radiation, spread across expanding space. This picture is often called heat death, though the name can be misleading. It does not mean everything becomes hot. In fact, it means the opposite of anything lively or useful happening. Heat death refers to a state where energy has become evenly spread out, with no meaningful differences left to drive change. Useful work depends on differences, hot and cold, dense and empty. High pressure and low pressure, a wound spring and an unwound one, a charged battery and a drained battery. Life depends on such differences too. Stars shine because they have gradients. Weather moves because Earth has temperature differences. Bodies live because they maintain order by using energy from food and sunlight. If the universe reaches a condition where energy is spread thinly and evenly, there may be no engines left, no cycles, no fires, no metabolism, no stars, no clocks in any useful sense. Time might still pass depending on what time means in such a state, but there would be almost nothing left to mark it. That is one possible answer to what happens after the end of the universe. Not a bang, not a collapse, not a final explosion, but a long approach to stillness. The universe does not end like a door slamming. It ends like a room cooling after the fire has gone out. At least, that is one leading possibility. Science is careful with words like certain, especially when discussing the fate of everything. The future of the universe depends on what the universe is made of, how dark energy behaves, whether protons decay, how gravity and quantum physics finally fit together, and whether there are parts of reality we have not yet understood. The honest answer is that we have strong models, but the far future remains a place where knowledge meets uncertainty. There are other possibilities. Some are dramatic. If dark energy changes over time in a particular way, the expansion of the universe could become more violent, eventually tearing apart galaxies, stars, planets, and even atoms in a scenario sometimes called the Big Rip. This is not currently the favoured outcome, but it remains an idea physicists have studied, because the nature of dark energy is still not fully known. Another possibility is a big crunch, where expansion eventually reverses and the universe collapses back inward. Current observations suggest the expansion is accelerating, which makes a future collapse less likely in the simplest models, but it remains part of the larger family of cosmic endings that science has considered. There are also bouncing universe ideas, where a collapse might lead to another expansion, perhaps another beginning. Some theories imagine new universes budding from old ones, or cosmic cycles stretching beyond what we call the Big Bang. These ideas are fascinating, but many remain speculative, waiting for evidence that may be difficult or impossible to obtain. So tonight, as we begin, we are not walking into one neat answer. We are entering a landscape of possibilities guided by the best science we have, but also by the humility that comes from asking a question almost too large for us. What happens after the end of the universe depends partly on what we mean by end. The end of stars is not the end of matter. The end of matter may not be the end of radiation. The end of useful energy may not be the end of existence. And the end of our ability to describe change may not be the end of whatever reality is at its deepest level. It may simply be the point where our usual language becomes tired and asks to sit down. But there is no need to rush toward that dark horizon. We can move slowly. We can begin with the universe we know, alive with stars and galaxies, and follow its future step by step. We can watch the bright era fade, the last stars burn low, the black holes take their long turn as the final major structures, and then ask what remains when even they are gone. Along the way, we will meet ideas that sound strange at first but become gentler when given time. Entropy, expansion, dark energy, proton decay, vacuum decay, black dwarf stars, Hawking radiation, heat death. These are large concepts, yes, but they are not here to frighten us. They are simply names we give to the universe as it grows older, and perhaps there is comfort in that. The universe is not a machine designed only for endings. It is a changing system, and change is what allowed stars to form, planets to cool, oceans to gather, chemistry to become biology, and biology to become someone listening in the dark, thinking quietly about where it all goes. The same laws that point toward a cold, far future also gave us this warm present. The same cosmic story that may one day fade into stillness has, for now, produced galaxies, laughter, questions, sleep, and the soft glow of a screen beside a bed. If the universe is temporary, then this moment is not less important. It is more specific. It is one small arrangement of matter and energy in which the cosmos has become aware enough to wonder about itself. So settle in, let your shoulders loosen, and allow the scale of the question to become spacious rather than heavy. We are going to start with the first great change in the far future, not the final darkness yet, but the slow quieting of the universe as star formation declines and the bright, familiar cosmos begins to age. For now, there are still stars everywhere, galaxies still shine, the night sky still carries ancient messages, but already in the background of the present universe the long trend is underway. Space is stretching, fuel is being used, the raw materials for new stars are gradually being locked away or scattered thin. The universe is not ending tonight or tomorrow, or in any span that human imagination handles comfortably. But it is moving steadily and silently toward a time when the great lights will become fewer, and the cosmic story will begin to sound much quieter than it does now. For now, the universe is still bright enough to fool us. Look up on a clear night, away from city lights, and the darkness does not seem empty at all. It is freckled with stars crossed by the pale mist of the Milky Way, and deep beyond what our eyes can see, filled with galaxies. There are spirals turning slowly, giant clouds of gas glowing where new stars are being born, old stars swelling, young stars burning fiercely, and black holes feeding in the crowded centres of galaxies. The universe today is not young in the way it once was, but it is still active. It still makes things. It still rearranges itself. It still has enough fuel, dust, gravity, and time to keep building bright places. Yet beneath all that activity, a slow change is already underway. The universe is beginning to grow quiet. Not quiet in the sense of sound, of course. Space is not carrying a neat little background hum from one galaxy to another, though it is pleasing to imagine the cosmos gently clearing its throat. This quiet is a decline in activity. It is the gradual slowing of star birth, the spreading out of matter, the loss of crowded conditions that once made the universe such a productive maker of light. A galaxy can look magnificent while already being past its busiest years, rather like a grand old theatre still lit for evening performances, even though fewer new actors are arriving backstage. We are living after the universe's most energetic youth. The great age of star formation has already passed. Stars are still forming, including in our own galaxy, but not at the rate they once did. The cosmos is still glowing, but it's no longer rushing to fill itself with new suns. To see why this matters, we have to picture what the early universe was like, not in all its strange details, but in its general mood. After the hot beginning expanded and cooled enough for atoms to form, the universe became mostly hydrogen and helium, the two simplest chemical elements. There were no stars at first, no planets, no galaxies with spiral arms, no glowing nebulae shaped like animals in telescope images, and certainly no one complaining that their phone battery was low. There was gas, gravity, darkness, and the slow gathering of structure. Tiny differences in density allowed some regions to pull in more matter than others. Over time, those regions grew. Gas collected, gravity tightened its grip. The first stars ignited. Those first stars may have been very different from most stars today. They likely formed from almost pure hydrogen and helium, with very few heavier elements mixed in, because heavier elements had not yet been made in large amounts. Many of those early stars may have been massive, bright and short-lived. They burned intensely, lived quickly, and died violently, scattering newly forged elements into space. Carbon, oxygen, silicon, iron, and many other ingredients were built in stars and spread by stellar deaths. This was one of the universe's great transformations. The cosmos started with simple raw material, then stars began cooking complexity into it. Later generations of stars formed from richer gas. Around some of them, planets could form. On at least one of those planets, chemistry eventually became biology, and biology eventually became a sleepy listener considering cosmic decline with admirable calm. For billions of years, this cycle of birth, light, death, and recycling filled galaxies with activity. Gas clouds collapsed into stars. Massive stars exploded and stirred their surroundings. Shock waves compressed nearby gas and triggered more star formation. Galaxies collided and merged, driving gas toward their centers and setting off bursts of new stars. In these crowded earlier times, the universe had more available fuel in the right places. It was denser than it is now. Galaxies were closer together. Encounters were more common. There was more cosmic weather, more turbulence, more mixing, more of the conditions that help gas fall inward and ignite. But every star that forms uses up some of the available gas. Some of that material returns to space when stars shed their outer layers, or explode, but not all of it returns in a form ready to make new stars. Some is locked inside long-lived stars. Some ends up in white dwarfs, neutron stars, and black holes. Some is blown out of galaxies by powerful winds from supernovae or energetic black holes. Some becomes too hot or too spread out to collapse easily. The universe is not a perfect recycling machine. It is more like a kitchen where some ingredients are reused, some are stored away, and some have rolled under the cupboard where no one wants to reach. Over time, the supply of cold, dense gas that can form stars becomes less abundant. This is one of the main reasons the cosmic future grows dimmer. Star formation depends on gas, especially cold gas gathered into dense clouds. A galaxy can contain a lot of matter, and still fail to make many new stars if that matter is too hot, too diffuse, or too stable against collapse. Gravity wants to pull gas together, but gas pressure, heat, turbulence, magnetic fields, and the motion of the galaxy all complicate the process. Star formation is not simply a matter of having material, it is a matter of having material in the right condition, in the right places, able to cool, clump, and fall inward until nuclear fusion begins in the core of a newborn star. Our own Milky Way still has such places. The great molecular clouds scattered through its disk are stellar nurseries, cold regions where stars can form. The Orion Nebula is one of the nearby examples, a glowing cloud where young stars are lighting up the gas around them. These regions are beautiful partly because they are temporary. A cloud can produce stars, but the stars it produces can also disrupt the cloud. Hot young stars blast radiation into their surroundings. Stellar winds push gas outward. Massive stars explode. The nursery does not stay peaceful. It is more like a room full of toddlers who have been given drums and a fog machine. Starbirth creates the conditions that eventually shut off or redirect more starbirth nearby. On the scale of a whole galaxy, this balance between fuel, gravity, heating, and disruption determines how active the galaxy remains. Spiral galaxies like the Milky Way often keep making stars for a long time because they retain gas in their disks. Elliptical galaxies, especially large ones, tend to be quieter. Many are dominated by older stars and contain relatively little cold gas. They can look reddish because their bright blue short-lived stars are gone, leaving longer-lived cooler stars behind. In a sense, they are already previews of the aging universe, full of stars but not full of new beginnings. They still shine, sometimes with enormous total brightness, but their light is mostly the glow of existing stars rather than the sparkle of ongoing creation. Another reason the universe grows quiet is the expansion of space itself. Expansion does not tear apart galaxies that are held together by gravity, but it changes the larger environment in which galaxies live. On the biggest scales, galaxies and galaxy clusters move farther apart. The cosmic web, that vast network of filaments and voids, becomes more stretched. Regions that are not gravitationally bound to one another become increasingly separated. Distant galaxies recede faster as space expands between us and them. Over very long times, many will pass beyond the cosmic horizon of any given observer. Their light, even if they continue to shine for a while, will no longer arrive. This is a subtle kind of loss. The galaxies do not all go out at once. They do not know they have become invisible from somewhere else. But from the point of view of future observers, the accessible universe shrinks. The local gravitationally bound region remains, while the rest fades from contact. For us, the Milky Way and Andromeda are moving toward each other and are expected eventually to merge, along with other members of our local group. That future merged galaxy may remain as an island of stars in an increasingly empty observable sea. Far beyond it, other galaxies will still exist for a time, but their light will be stretched and weakened and then effectively unreachable. The universe becomes not only dimmer, but lonelier. This has an interesting consequence. A civilization arising in the far future, after distant galaxies have disappeared beyond its horizon, might have a much harder time discovering the history of the universe. Today, we can see evidence of cosmic expansion. We can observe distant galaxies, the cosmic microwave background, and the large-scale structure of the universe. We can reconstruct a story of a hot, dense early state and a long evolving cosmos. Future astronomers in an isolated galaxy might look out and see mostly local stars, with little evidence of the vast expanding universe beyond. The clues would not be entirely gone, perhaps, but they would be far less obvious. It is a reminder that science depends not only on intelligence, but on timing. We happen to live in an era when the universe is old enough to contain heavy elements, planets, and life, but young enough that the wider cosmos is still visible. That is a remarkable window. We are not at the beginning and not near the end. We are somewhere in the long middle when the lights are still on, and the evidence has not yet drifted away. The quieting of the universe is also tied to something called entropy, though we can keep the idea simple. Entropy is often described as disorder, but for our purposes tonight it is helpful to think of it as the spreading out of energy and the fading of useful differences. Stars shine because matter is concentrated and hot in their cores, while space around them is colder. Life uses energy because there are differences to exploit. A cup of hot tea cools because its heat spreads into the room. It never spontaneously gathers that heat back into itself and becomes hot again, which is disappointing but at least consistent. In the same broad way, the universe evolves from states with strong differences towards states where energy is more spread out. The early universe was strangely smooth in some ways, but it allowed gravity to build stars and galaxies, creating concentrated pockets of heat and structure. Those pockets then spend energy into space. Over time, the ability to keep making new concentrated sources of energy declines. This does not mean nothing interesting will happen soon. The timescales are enormous. The Milky Way will continue forming stars for a long time. Some small red dwarf stars being born now may shine for trillions of years. The future is not a sudden power cut. It is more like a town where fewer new houses are built each century, while the old ones remain occupied for a very long time. From a human perspective, the universe is still lavish with light. Even the quieting process is so slow that it might as well be stillness compared with a lifetime. But on the cosmic scale, the trend is clear. The era when the universe made stars most vigorously is behind us. The stars themselves help determine how long the light lasts. Massive blue stars are spectacular, but they are not patient. They burn through their fuel quickly and die after only millions of years. Smaller yellow stars like our Sun live for billions of years. Red dwarfs, smaller and cooler, can live for far longer than the current age of the universe. Because red dwarfs are efficient and common, they will be the steady lamps of the far future. When the bright, massive stars are long gone and sun-like stars have become remnants, red dwarfs will continue to burn quietly. They are not dramatic. They do not dominate the sky with the same brilliance as giant stars, but they endure. If the future universe has a working motto, it might be something like, "The small, careful flames last longest." Around some red dwarfs there may be planets. Whether such planets can remain habitable for extremely long times is a complicated question. Red dwarfs can be active, especially when young, producing flares that may challenge atmospheres. Planets close enough to be warm may become tidally locked, with one side always facing the star. Yet over long times, some worlds may find stable conditions. If life can adapt to such environments, red dwarfs could provide some of the last natural homes for biology in the stellar era. This is one reason the far future is not simply empty darkness right away. It may contain long quiet ages around dim stars, with possibilities very different from life under a sun like ours. Still, even red dwarfs have endings. They slowly consume their hydrogen. Because they are fully mixed inside, they can use their fuel more efficiently than larger stars, which helps them last so long. But eventually they too will fade. No star is a permanent solution to darkness. The universe can stretch the process almost beyond imagination, but it does not stop it. When the last red dwarfs finally exhaust their fuel, the familiar age of shining stars will end. That moment lies so far in the future that our usual words begin to lose their grip. We can say trillions of years and then keep going, but the mind does not truly picture such spans. It treats them like large bags labelled with large words and politely declines to unpack them. Before that happens, galaxies themselves will continue to change. The Milky Way and Andromeda will merge in several billion years, forming a larger galaxy. During such mergers, stars rarely collide directly because the spaces between them are immense, but gas clouds can interact, and gravitational forces can rearrange orbits. The night sky from a planet existing during that era would be extraordinary, though perhaps not peaceful for every local system. Over time, the merged galaxy would settle. Star formation may be triggered during parts of the merger, then decline as gas is used up or heated. The final result may be a large, more elliptical system, with older stars and less new star formation. It would be a grand structure, but less fertile than the star-forming disk we know today. Even within galaxies, stars do not stay neatly arranged forever. Over immense times, close encounters between stars can gradually alter their orbits. Some stars may be flung outward into intergalactic space, others may sink toward the centre. Stellar remnants can interact, black holes can merge. The galaxy becomes less like a stable city and more like an old crowd slowly dispersing after a very long evening. None of this happens quickly. A star could orbit the galaxy hundreds of thousands or millions of times before these subtle effects add up. But given enough time, even rare events become important. The far future belongs to patience. As the universe grows quieter, it also becomes colder in a broad sense. The cosmic microwave background, the afterglow of the early universe, continues to be stretched by expansion. Today it is already very cold, just a few degrees above absolute coldness. In the future, it will become colder still, its radiation stretched to longer and longer wavelengths. This background was once hot enough to fill all space with a glow. Then it cooled into microwaves. Later it will become even weaker and more diffuse. Another ancient clue will fade toward undetectability. The universe keeps its records, but not forever in forms easily read. There is something humbling about this. We often think of the universe as a place of endless creation, because the part we see is full of stars and galaxies. But creation in the universe is tied to conditions, and conditions change. Star formation is not guaranteed forever. Visibility is not guaranteed forever. Even the evidence of the beginning is not guaranteed to remain clear for every future observer. We are living during a bright and informative era, and that makes our curiosity feel strangely lucky. The universe has given us enough darkness to see the stars, enough stars to make chemistry rich, enough time for life to appear, and enough remaining cosmic evidence to ask where everything came from and where everything is going. This does not make the future tragic. The universe is not failing. It is evolving according to the same laws that made its earlier beauty possible. A star that burns fuel is not doing something wrong by eventually running out. A galaxy that slows its star formation is not losing a contest. The quieting of the universe is simply the long consequence of energy being spent, matter being locked away, and space expanding. It is not a moral story. It is physics. And physics, even when it points toward darkness, can be oddly reassuring, because it replaces vague fear with a process we can follow. The lights do not go out because the cosmos becomes angry or bored. They fade because fuel is finite, structures change, and time is very, very long. There is also comfort in scale. The future quieting of the universe does not cancel the present. If anything, it makes the present more vivid. We live while stars are still being born. We live while galaxies are still visible in every deep telescope image. We live while the sky still contains both young blue stars and ancient red ones, bright nebulae and cold dust, exploding stars and quiet planets. We are here during the universe's long afternoon, not its midnight. There is still warmth in the room. The kettle has not gone cold yet, though on cosmic timescales it is perhaps beginning to think about it. So as we follow the universe forward, the first great change is not a sudden ending but a slowing rhythm. Fewer new stars, less cold gas gathered into bright nurseries, more matter sealed inside remnants, more galaxies aging into redder, quieter forms. More of the distant universe slipping beyond view as expansion continues. The cosmos becomes less crowded with beginnings. Its activity declines not because one switch is turned off, but because countless small processes all lean in the same direction. Fuel is used, energy spreads, distances grow. The grand machinery continues, but its most brilliant phase begins to pass. For a while, this quiet universe will still be beautiful. The skies of future worlds may still hold stars. Some galaxies will still glow. Red dwarfs will still burn with steady patience. White dwarfs will cool like old embers. Black holes will wait in galactic centers, not yet the final rulers of the cosmic dark, but already gathering significance. The universe will not be empty, not yet. It will be older, calmer, less fertile, more spacious. And as the last great waves of starbirth fade into memory, attention naturally turns to the stars that remain, especially the smallest ones, the ones that know how to spend their fuel slowly, as if they understand better than any giant that in a universe growing quiet, endurance becomes its own kind of light. By the time the universe has grown old enough for its brightest star-forming years to fall far behind it, the sky would no longer look like the sky we know. There would still be stars, yes, but fewer of the brilliant blue giants that make young galaxies sparkle in telescope images. Those massive stars are extravagant creatures. They burn hot, live quickly, and leave behind dramatic ruins. They are the celebrities of stellar life, arriving with glare, making a scene, and departing before anyone has quite finished adjusting the camera. In the far future, they will be gone. The stars that remain will be the quiet ones, the careful ones, the small red dwarves that spend their fuel so slowly they seem almost reluctant to change at all. These red dwarves are easy to overlook because they are faint. None can be seen with the unaided eye from Earth, even though they are the most common stars in the galaxy. They do not blaze like Sirius or shine like Vega. They do not flood their surroundings with the fierce blue-white light of massive young stars. They glow with a modest reddish light, small, cool, and patient. But in the long future of the universe, patience matters more than brilliance. A massive star may live only a few million years. A star like our Sun lasts for billions. A small red dwarf can last for trillions upon trillions of years. If the universe were a long winter night, red dwarfs would be the embers that keep glowing after the great logs have burned down. Their longevity comes from how efficiently they use their fuel. Larger stars have hot, crowded cores where fusion races ahead, but much of their hydrogen can remain in outer layers that never fully participates in the central burning. Red dwarfs are different. Because of their internal structure, many of them can circulate their material throughout much of the star, giving them access to a larger fraction of their hydrogen supply. They burn slowly and thoroughly, like a careful candle rather than a bonfire. This means that long after stars like the Sun have swollen, shed their outer layers, and become white dwarfs, the smallest red dwarfs will still be there, glowing faintly in a darkening cosmos. Imagine a future world orbiting one of these stars. The universe beyond its local system would be far less lively than ours. Distant galaxies may have slipped beyond view because expansion has carried them too far for their light to reach. The local galaxy may be old, reddish, and mostly quiet, with little fresh gas left to form new stars. The skies would contain many ancient stellar remnants, but not many bright young suns. Around a red dwarf, daylight would be dimmer and redder than on Earth. If a planet were close enough to stay warm, its star might loom larger in the sky, glowing like a deep coal rather than a golden disk. Such a planet might be tidally locked, keeping one face toward the star and the other turned permanently away. One side could rest under a steady red day, the other under endless night, with a twilight region between them where conditions might be more balanced. It is not the kind of place most holiday brochures would lead with, but the universe in old age may not be overly concerned with tourism. Whether life could survive around red dwarfs for such extreme spans is an open and complicated question. Young red dwarfs can be restless, producing powerful flares that may strip atmospheres from nearby planets or bathe them in harsh radiation. Planets close to these stars may face difficult conditions, but over long times, some systems may settle. Atmospheres, magnetic fields, oceans, geology, and luck would all matter. If life can adapt to red dwarf environments, then such stars may offer the last long natural homes for biology in the universe. Long after sun-like stars are gone, small organisms, or perhaps something more complex, could still be living under faint red light, completely unaware that they are part of the late evening of cosmic history. As these red dwarfs age, they will not become red giants in the same way the sun will. Our sun, after using much of the hydrogen in its core, will swell into a giant, changing the inner solar system dramatically before shedding its outer layers. The smallest red dwarfs behave more quietly. They slowly convert hydrogen to helium, growing gradually warmer and brighter for a time, though still modest compared with larger stars. Eventually, after almost unimaginable stretches of time, they too exhaust their fuel. They will contract and fade into dense remnants. Because the universe is currently far too young, no red dwarf has yet reached this final state. Every red dwarf that has ever formed is still, in some way, still burning. That fact is worth resting with for a moment. We live so early in the full life of the smaller stars that none of them has had time to die. When the final red dwarfs fade, the universe crosses an important threshold. The age of ordinary starlight comes to an end. Not the end of every glow, not the end of every physical process, but the end of stars as we normally understand them, those self-shining spheres powered by nuclear fusion. For a universe that has spent most of its familiar history lit by stars, this is a profound quieting. It is as if the last village lamps have gone out one by one across an enormous countryside. There may be no single observer watching the last star fade, and perhaps no one left to mark the occasion. But as a physical transition, it matters. The universe after the last stars is different from the universe before them. It is no longer a place where new sunlight can be counted on to arise from gas clouds. It becomes a realm of remnants. The remnants come in several kinds. White dwarfs are the collapsed cores of stars like the Sun, dense objects made mostly of carbon and oxygen, slowly cooling after their active lives are done. They begin hot, sometimes extremely hot, but they no longer produce energy through fusion in the ordinary steady way. They simply radiate their stored heat into space. Over vast ages they dim. At first they may glow white, then yellowish, then red, then infrared, and eventually become cold dark bodies often called black dwarfs. No black dwarfs exist yet as far as current science expects, because the universe has not lasted long enough for a white dwarf to cool that far. They belong to the future, a population of dead stars waiting for time to make them. A black dwarf would not be a black hole. It would not trap light by gravity. It would simply be cold and dark, a stellar ember that has finally lost its warmth. It would still have mass. It would still exert gravity. It might still have planets, though most such planets would be frozen beyond recognition unless warmed by some unusual internal process or gravitational interaction. Around a black dwarf, there would be no sunrise, no photosynthesis, no ordinary daylight. A planet orbiting one would move through darkness beside the faint corpse of a star. It sounds bleak, but again, the universe is not being bleak on purpose. It is following the consequences of energy being radiated away. There are also neutron stars, the dense remnants of massive stars. These are stranger and more extreme than white dwarfs. A neutron star packs more mass than the Sun into a sphere roughly the size of a city. Its gravity is immense. Its matter is crushed into states that challenge ordinary intuition. Many neutron stars begin as pulsars, spinning rapidly and sending beams of radiation into space. Over time, they slow. Their magnetic fields may weaken. Their radiation fades. In the far future, many neutron stars will become cold, dark relics, still dense, still gravitationally powerful, but no longer announcing themselves with bright pulses. They will be like cosmic lighthouses whose lamps have finally worn out. Brown dwarfs also play a role in this late story. They are sometimes called failed stars, though that feels a little unfair. Not everything must become a star to be respectable. Brown dwarfs form like stars from collapsing gas, but they do not have enough mass to sustain normal hydrogen fusion in their cores. They glow faintly from leftover heat when young and then cool with time. The universe may contain enormous numbers of them, drifting quietly between true stars and giant planets. In the far future, brown dwarfs will be cold and dark, but they may still occasionally interact. Given enough time, Rare encounters between brown dwarfs might merge them into objects massive enough to ignite as new, small stars. This would be a strange late flicker in a universe otherwise past its stellar youth. A couple of dark, almost stars wandering for ages, meeting by gravitational chance and briefly giving the universe one more lamp. Such events would be rare, but in the deep future, rare does not mean impossible. Time becomes so vast that processes too unlikely to matter today can become part of the long background story. Stellar remnants can pass near one another, orbits can shift, objects can be ejected from old galaxies, white dwarfs can collide, neutron stars can merge, black holes can swallow whatever strays too close. A dead or dying galaxy is not perfectly still, it is simply slow. The old stars and remnants move through one another under gravity, like a crowd thinning after a festival, with occasional meetings, accidents and departures long after the music has stopped. There may also be a final kind of star that appears because of collisions or mergers, rather than normal star formation. If two brown dwarfs combine, or if certain low-mass objects gather enough material, a faint star might ignite in the dark era. These late stars would be among the last true fusion-powered lights. They would not restore the universe to its former brightness. They would be more like sparks from cold ashes, brief by the standards of the future, though still perhaps long-lived by any human measure. Their appearance would remind us that cosmic endings are not perfectly tidy. The universe does not move from bright to dark in a neat straight line. It fades with afterglows, delays, exceptions, and faint surprises. For planets, the fading of the last stars would be the end of ordinary habitability. Planets rely on energy. A world like Earth is warmed mainly by its star. Remove sunlight, and the surface eventually freezes. Internal heat from radioactive decay and leftover formation energy can last for a long time, especially in large rocky planets or moons with tidal heating. But these sources are limited. Some worlds may keep subsurface oceans beneath thick ice for far longer than their surfaces remain friendly. Even today, moons like Europa and Enceladus suggest that liquid water can exist far from direct sunlight if internal heating is available. In the far future, such hidden environments might be among the last natural places where simple life could persist. Not under blue skies, not under forests, but under ice, in dark oceans warmed by the slow flexing of rock or the fading heat of a planet's interior. Yet even those shelters cannot last forever. Radioactive materials decay, tidal arrangements change, planetary interiors cool, atmospheres freeze or escape. Orbits can be disrupted by passing stars or remnants. A planet may be flung into interstellar space, becoming a rogue world drifting without a sun. Some rogue planets might retain thick atmospheres or internal oceans for long periods. A thick blanket of hydrogen, for example, could trap heat and keep a surface or subsurface environment warmer than expected. This is one of those ideas that makes the universe feel both harsher and more inventive. Life, if it exists elsewhere, may not be limited to sunny worlds. It may hide in places that seem dark from the outside, living on chemistry, heat, and patience. Still, the decline of starlight would place severe limits on complexity. Large ecosystems like those on Earth depend on a strong flow of energy. Sunlight drives photosynthesis, which supports food chains, atmospheric chemistry, and the large-scale activity of the biosphere. Without stars, the energy available to life becomes scarce. Simple organisms might endure in protected niches, but the long-term future would become increasingly difficult for anything requiring abundant energy. Civilizations, if any exist in those eras, would face the same basic issue. Intelligence does not remove the need for usable energy. It only makes the search for it more creative, and possibly more dramatic. A sufficiently advanced civilization might gather around long-lived red dwarfs, tap black holes, harvest energy from stellar remnants, or engineer habitats around remaining sources. But even cleverness must work with physics. There is no unlimited pantry hidden behind the cosmic cupboard. As the last stars fade, the appearance of the universe would change in ways almost impossible to visualize from our bright era. The glowing bands of galaxies would dim as their stars die. The blue light of young stars would have vanished first, followed by the steady light of sun-like stars, and eventually the faint red light of the smallest stars. What remains would be dark objects separated by immense distances. White dwarfs cooling into black dwarfs. Neutron stars slowing and freezing. Brown dwarfs reduced to cold masses. Planets orbiting dead suns or wandering alone. Black holes waiting. Growing through rare encounters, or simply persisting in the dark. This period is sometimes called the degenerate era, because much of the matter left in stellar remnants exists in forms supported by quantum pressure rather than ordinary heat from fusion. That phrase sounds a little rude, as though the universe has taken up bad habits in old age, but in physics it has a specific meaning. White dwarfs and neutron stars are held up by the behavior of particles under extreme compression. They are not ordinary glowing gas balls like stars. They are compact remains, strange objects that show what matter becomes after stellar furnaces shut down. The universe of that era is not empty. It is physically rich, but it is no longer warm and shining in the familiar way. One of the deepest questions about this future is whether matter itself is stable forever. Protons, which are found in the nuclei of atoms, may or may not decay over enormous timescales. Experiments have not observed proton decay, and if it happens, it must be incredibly rare. But some theories beyond the current standard understanding of particle physics suggest it might occur eventually. If protons decay, then ordinary matter has a deeper expiration date. Atoms would not last forever. Planets, black dwarfs, and many remnants would slowly lose their substance as their particles transformed into lighter products and radiation. Matter would not simply sit in the dark eternally. It would gradually dissolve at the most basic level. If protons do not decay, the future changes. Matter can persist much longer in cold forms. Black dwarfs, planets, and other remnants might remain for staggering durations, though they would still be subject to rare quantum processes, gravitational encounters, and eventual swallowing by black holes in some cases. This is one reason the far future contains uncertainty. We can make strong predictions about stars using well-tested physics, but the fate of matter over unimaginable times depends on questions we have not fully answered. The end of starlight is clear in broad outline. What happens to the cold remains afterward is less certain. Even if matter stays stable, the lack of stars changes the meaning of time for any possible observer. Clocks require processes. A clock can be a swinging pendulum, a vibrating atom, a rotating planet, a beating heart, or a changing orbit. In a dark universe of cold remnants, processes still occur, but more slowly and less usefully. Without day and night, without seasons, without stellar cycles, time becomes harder to experience in familiar terms. A being living in such an era, if any could, might measure time by orbital motion around a dark mass, by internal mechanical systems, by particle decay, or by the slow cooling of its environment. But the natural rhythms that shaped life on Earth would be gone. No sunrise, no year marked by warmth and cold, no stars born in glowing clouds. The universe would still have sequence, but less drama. And yet, thinking about the last stars can make our current stars feel more generous. Every sunrise is part of a finite era. Every patch of daylight is produced by a star that has a lifetime. The sun is not merely a background feature of our days. It is a temporary source of order and warmth in a universe where such sources are precious. The stars overhead are not permanent decorations. They are active faces in the lives of matter. They are how the universe spends part of its stored possibility. One day, the last of them will fade, but the fact that they shine at all is astonishing. It is tempting to imagine the final star as a single, lonely object, glowing red against total darkness. In reality, the last stellar lights may be scattered across vast regions, some born naturally as long-lived red dwarfs, others created later by rare mergers. There may not be a clear final star in any practical sense. Different regions will have different histories. Some small stars will outlast others. Some late collisions may produce new lights after many have gone. But eventually, however uneven the process, true stars will cease. The universe will stop making ordinary fusion-powered suns. The last faint red glows will weaken. The final warm planets, if any remain, will lose their skies to cold. The stellar age will become a closed memory, stored only in remnants, radiation, and whatever records may somehow endure. From there, the balance of importance shifts. During the age of stars, black holes are fascinating but not alone. They share the cosmos with bright suns, glowing gas, planets, and galaxies full of light. After the last stars fade, black holes become far more central to the story. They are not alive, not intentional, not hungry in the way stories sometimes describe them, but they are the strongest remaining gravitational structures. They can persist for lengths of time that make even red dwarfs seem brief. In a dark universe of cooled remnants, black holes may become the final major engines of change, the last places where gravity gathers matter, the last objects capable of producing significant energy when something falls in, or when they slowly evaporate through quantum effects. So the fading of the last stars is not the final stop. It is a handover. The universe moves from the era of shining furnaces to the era of dark remnants and black holes. The light does not vanish all at once. It thins, reddens, cools, and dwindles across timescales beyond ordinary thought. The small stars take their long turn, then give way. White dwarfs become black dwarfs. Neutron stars fall silent. Brown dwarfs cool. Planets freeze. Rare sparks may still appear from collisions, but they too are temporary. And as the last natural starlight drains from the universe, the great dark objects that once hid in the centres of galaxies and the ruins of massive stars remain, waiting through the silence, becoming the final lanterns, not because they shine like stars, but because in the deep future, even their strange faint ways of giving up energy may be the closest thing the universe has left to fire. In that long dark age after the last ordinary stars have faded, black holes become some of the most important objects left. They do not become important because they are friendly, bright, or especially sociable. A black hole is not the kind of neighbour that lends you a cup of sugar. It is important because it lasts. When most stars have cooled into dark remnants, when planets have frozen or drifted away, when galaxies have aged into dim collections of dead suns and compact objects, black holes remain as deep gravitational wells in the dark. They are not empty holes in space, despite the name. They are regions where matter has collapsed so intensely that once something passes a certain boundary, light itself cannot escape back out. From the outside, that boundary marks the point of no return. Beyond it, our usual idea of escape stops being useful. During the bright age of the universe, black holes can seem like strange side characters, dramatic but not dominant. We notice them when they feed on gas, tear apart stars, or sit in the centres of galaxies with enormous masses. We infer them from the motions of nearby stars, from glowing disks of matter heated as it spirals inward, from jets of particles launched at high speeds, and from gravitational waves released when black holes merge. They are already powerful today, but they share the cosmic stage with stars. Stars do most of the shining. Stars warm planets. Stars forge elements. Stars provide the visible structure that makes galaxies glow. Black holes often reveal themselves only when something nearby gives them material to work with. Without falling gas or unlucky stars, they can be almost perfectly dark. In the far future, that balance changes. Stars disappear as active engines. The bright furnaces shut down. The small red dwarfs, after their astonishingly long lives, finally exhaust their fuel. White dwarfs cool toward black dwarfs. Neutron stars become quiet. Brown dwarfs lose their heat. Planets become cold bodies drifting through old systems or wandering between them. In such a universe, black holes stand out not because they shine by themselves in the usual way, but because they remain capable of concentrating matter and producing energy under the right circumstances. If anything falls toward a black hole, the region outside the event horizon can become one of the last places where the universe still makes a noticeable display. That display does not come from inside the black hole. The black hole itself does not let light out from within the horizon. The light comes from matter before it crosses that boundary. When gas, dust, a star, or a compact remnant falls toward a black hole, it does not usually drop straight in like a pebble into a pond. It often spirals around, forming a disk. Friction, collisions, magnetic fields, and the violent stretching of gravity heat that material. It can become extremely hot and bright. In the earlier universe, this process powers quasars and active galactic nuclei, some of the brightest objects ever observed. A black hole feeding efficiently can release more energy from falling matter than ordinary nuclear fusion releases inside stars. That is not because the black hole is burning fuel like a star. It is because gravity near a black hole is very good at turning the energy of motion into heat and radiation. In the very distant future, there will be far less loose gas available, so the great blazing disks of the early and middle universe will become rare. Still, black holes may occasionally feed. An old star remnant might pass too close. A cold planet might be perturbed from its orbit and fall inward. Two compact objects might interact in a decaying old galaxy, sending one into the central black hole. When that happens, the black hole can briefly become a lantern in the dark, surrounded by a hot disk or a burst of radiation from disrupted matter. These events would be separated by immense quiet intervals, but the universe of black holes is not completely still. It is a place where rare encounters matter because time has become so abundant that even the unlikely eventually gets its turn. Large black holes already sit in the centres of many galaxies. Our own Milky Way has one, with a mass millions of times greater than the Sun. Other galaxies contain central black holes with masses of billions of suns. In the long future, as galaxies merge and age, their central black holes can also merge. When two galaxies combine, their central black holes gradually sink toward the new centre through interactions with stars and gas. Eventually they may form a pair, orbit one another, and then merge into a larger black hole. The final moments of such a merger release gravitational waves, ripples in space-time that carry energy outward. These waves do not need a bright environment to exist. Even in a dark universe, black hole mergers can send out gravitational signals, though who or what could detect them in that distant era is another question entirely. The centres of old galaxies may therefore become dominated by enormous black holes, grown through mergers and occasional feeding. Around them, a swarm of stellar remnants could continue orbiting for a long time. White dwarfs, neutron stars, black dwarfs, brown dwarfs, planets, and smaller black holes would move through the gravitational field, sometimes passing near one another, sometimes being flung away, sometimes falling inward. A galaxy in this era is less like a shining city and more like an old dark harbour where heavy objects drift slowly through enormous space. Most of the time, nothing much happens. Then, after spans so long that ordinary words begin to look embarrassed, something passes too close to the central black hole, and the darkness briefly remembers how to glow. Smaller black holes also remain, some formed from the deaths of massive stars, others may have formed through mergers. There may even be primordial black holes, if such objects were created in the very early universe, though that remains uncertain. Stellar mass black holes can wander through galaxies or orbit in systems with other remnants. If they encounter matter, they can feed. If they encounter other black holes, they can merge. If a black hole passes through a region containing cold objects, it may disrupt or capture them. But most black holes will spend almost all their time doing very little from the outside point of view. This is one reason the far future is so strange. The most important objects left are also, for most of their lives, quiet. Calling black holes final lanterns is therefore a little unfair and a little accurate. They are not lanterns in the simple sense. A lantern has fuel inside and gives light outward. A black hole hides its interior and only glows through what happens around it, or through a much subtler process that becomes important much later. But compared with black dwarfs and frozen planets, black holes can still generate intense radiation when matter falls toward them. They can still create gravitational waves when they merge. They can still shape the motion of the last cold objects in old galaxies. In a universe where ordinary stars are gone, that makes them some of the last engines of visible change. There is a common idea that black holes are cosmic vacuum cleaners, roaming through space and sucking up everything nearby. This is not quite right. A black hole has gravity like any other object with the same mass. If the Sun were somehow replaced by a black hole with the same mass, Earth would not immediately spiral into it. We would lose sunlight, which would be a considerable inconvenience, but our orbit would remain roughly the same. Black holes are dangerous if you get very close, because their gravity changes sharply over short distances, and because the event horizon marks a one-way boundary. But they do not pull in the entire universe by magic. In the far future, many objects will orbit black holes for enormous lengths of time without falling in, just as planets orbit stars today. Over very long times, however, gravitational interactions can slowly rearrange things. In an old galaxy, objects repeatedly tug on one another as they pass. Most encounters are distant and weak, but over huge timescales they add up. Some objects gain energy and are thrown outward. Others lose energy and sink inward. This process can cause many stars and remnants to escape from galaxies, leaving behind fewer objects bound to the central black hole. A portion of the remaining material may eventually fall in. The galaxy slowly evaporates in a gravitational sense, not because its objects turn into vapor, but because repeated encounters scatter them away. The central black hole grows a little from what it captures, while many other remnants drift into the widening dark between galaxies. This future is extremely sparse. Distances between objects become enormous. If you were somehow placed in that era, safely and magically equipped with a very patient spacecraft and excellent snacks, you might travel for ages through darkness before passing anything substantial. The sky would not be full of stars. It would be mostly black, with perhaps faint radiation and occasional distant events. A feeding black hole would be rare enough to be precious, a temporary source of light in a universe that had almost forgotten brightness. But it would also be hostile, surrounded by strong gravity and intense radiation. Beautiful from a safe distance, not recommended as a picnic location. The largest black holes would last the longest. This may feel backwards at first. In ordinary life, large fires often burn through fuel quickly, while small things cool faster. Black holes follow their own strange rules. Through a quantum process associated with their horizons, they are expected to lose energy very slowly. Smaller black holes radiate more strongly and disappear sooner. Large black holes radiate extremely weakly and can survive for staggering lengths of time. A black hole with the mass of a star lasts far beyond the current age of the universe. A supermassive black hole can last much, much longer still. So when everything else has faded, the giant black holes at the centres of old galaxies may be among the final large structures left. This slow loss of energy is known as Hawking radiation. It comes from the combination of quantum theory and the presence of an event horizon. The full explanation is subtle, but the simple version is that black holes are not perfectly eternal. They have a temperature incredibly tiny for large black holes, and they can radiate. For black holes today, this radiation is so weak that it is completely overwhelmed by the cosmic background radiation and any surrounding matter. A black hole today gains more energy from its environment than it loses through this process. But in the far future, after the universe has expanded and cooled, after stars are gone and background radiation has thinned, Hawking radiation becomes the main way black holes change. They begin, very slowly, to evaporate. Before that evaporation dominates, black holes spend an enormous era as dark gravitational anchors. They may absorb the last bits of matter that remain bound to them. They may merge with other black holes. They may be surrounded by faint debris, cold remnants, or almost nothing at all. The universe becomes a kind of black hole age, where these objects outlast nearly everything that once made the cosmos familiar. If the stellar era was the age of shining furnaces, this is the age of sealed vaults. Matter that falls in is hidden behind horizons. Information about it becomes part of one of the deepest puzzles in physics. Energy can still come out through radiation over unimaginable time, but the details of how black holes store and release information remain an active area of scientific debate. That debate matters because black holes sit at the meeting point of gravity, thermodynamics, and quantum mechanics. They are not just astronomical objects, they are tests of our understanding of reality. A black hole has entropy, which means it has a connection to information and disorder. It has a temperature, though for large black holes the temperature is almost absurdly low. It warps time strongly near its horizon. It forces physics to deal with extreme conditions where our best theories do not yet fit together perfectly. In the far future, when black holes dominate the universe, the fate of everything becomes tied to questions physicists are still trying to answer today. The end of the universe is not only an astronomy question, it is also a quantum gravity question wearing a very large dark coat. For an outside observer, time near a black hole behaves strangely. Clocks closer to a black hole run more slowly compared with clocks far away. If something falls toward the event horizon, an observer far away sees it appear to slow and fade, its light stretched and weakened. The falling object itself, ignoring all practical dangers, would cross the horizon in a finite experience of time. This difference is one of the reasons black holes feel so unsettling. They do not simply sit in space, they alter the relationship between time, gravity, and observation. In the deep future, when black holes are among the last remaining structures, time itself would be measured against objects that bend it severely. Black holes can also spin. Many likely do. A rotating black hole drags the space around it, creating an environment where matter and energy behave in extreme ways. Energy can, in principle, be extracted from a spinning black hole under certain conditions. Advanced civilizations, if they existed in the far future, might see black holes not only as hazards, but as energy sources. They might feed matter into them carefully, use accretion disks, exploit rotation, or build vast structures nearby to harvest power. This is speculative, of course, but it follows a basic point. In a universe where stars are gone, any remaining concentrated source of usable energy becomes valuable. Black holes, especially spinning ones, could be among the last natural reservoirs from which work can be extracted. There is something almost practical about this thought. A civilization trying to survive deep time would have to think like a careful accountant. How much usable energy remains? How slowly can it be spent? What processes waste the least? What environments remain stable? A star is a generous but temporary provider. A black hole is far stranger. It can be dangerous, difficult, and dim unless fed, but it can endure. If such civilizations ever exist, they may gather around black holes as earlier life gathered around stars. Not for warmth in the simple daylight sense, but for access to gravitational energy and long-term survival. The image is not of cities under blue skies, but of engineered habitats in deep darkness, orbiting at safe distances from a massive object that cannot be seen directly, living by the energy released from carefully managed matter falling toward the horizon. It is not cozy in the usual cottage sense, but give it a kettle and some soft lighting, and perhaps one could manage. Eventually, though, there will be less and less matter left to feed them. Objects will be swallowed, ejected, decayed, or scattered beyond reach. The black holes will sit in expanding darkness, losing energy by hawking radiation at a pace so slow that the word slow feels badly underprepared. Smaller black holes go first, stellar mass black holes evaporate over immense times, supermassive black holes remain far longer. Their radiation is faint, cold, and low energy for most of their lives. They do not blaze like stars, they leak away. Only near the very end of a black hole's evaporation does it become hotter and release energy more rapidly. The final moments may involve a burst of particles and radiation, though the exact details depend on physics at energies where our understanding is incomplete. So in the black hole era, the universe has a strange shape to its story. For most of the time, black holes are nearly silent. Rare feeding events and mergers provide flashes of activity. Then, across vastly longer times, hawking radiation slowly takes over. The objects that once seemed like ultimate prisons begin to give themselves back to the universe, not as the stars they swallowed, not as planets restored, but as thin radiations spreading through space. In a sense, black holes are not permanent tombs, they are extremely patient delays. They take matter and energy out of ordinary circulation for almost unimaginable durations, then release energy back in a diluted form. The universe does not get its old structure back, it gets a colder, thinner aftermath. This is why black holes can be called the final lanterns, but also why the phrase carries a quiet irony. They are final lights in a universe with almost no light left, yet their own direct glow is weakest when they are largest and longest lived. They become important not by shining steadily, but by outlasting, by concentrating gravity, by occasionally feeding, by merging, and finally by evaporating. They are not the cheerful lamps of the stellar age. They are the last deep mechanisms through which the universe can still produce noticeable change after stars have finished their work, and as they take over the far future, they change the emotional texture of the cosmic story. The earlier universe is full of birth. Gas clouds collapse, stars ignite, planets form, chemistry grows complex. The black hole era is more about storage, waiting, and slow release. Matter is no longer gathering into new suns. It is being hidden, scattered, cooled, or swallowed. Activity becomes rare. The universe becomes less like a forest growing under sunlight and more like an old archive, where most of the books are locked away in rooms no one can enter, and the lights switch on only when some ancient mechanism stirs. Still, this is not nothing. A black hole in the far future is a reminder that the universe does not end when the stars end. Gravity continues, quantum effects continue, horizons continue to matter, the old remnants still move, rare encounters still happen, energy still changes form. The cosmic story becomes quieter, but not completely blank. The final lanterns burn strangely, sometimes through matter heated outside the horizon, sometimes through mergers shaking spacetime, and ultimately through the faint quantum radiation that slowly drains them. Their age is long, dark and difficult to picture, but it is part of the same continuous future that begins with the stars we see tonight. After the last star has faded, these black holes remain scattered through the enormous dark, some small by cosmic standards, some vast beyond easy imagination, each carrying the mass of what it has swallowed and the history of the galaxy that shaped it. For ages they wait, occasionally disturbed, occasionally fed, slowly losing the contest with the emptiness around them. And once the surrounding universe has become cold enough and the background has thinned enough, their faint evaporation becomes the main event, a process so gradual that it makes the lifetime of every star seem brief, yet still not endless, because even the darkest giants have a future in which they begin to shrink. For most of their lives, black holes do not look like objects that are losing a contest. They seem like the winners of gravity. Stars can burn out, planets can freeze, galaxies can become old and dim, but a black hole appears to remain silent and absolute, keeping whatever has crossed its horizon hidden from the rest of the universe. If the far future has a monument, it is tempting to imagine it as a black hole, massive, dark and patient, sitting in the middle of an ancient galaxy long after the last red star has faded. But the universe has a habit of making even its most permanent-looking things temporary. The black hole, that deepest vault, that final gravitational night, is not quite forever. The reason is one of the strangest ideas in modern physics. Black holes can slowly evaporate. Not evaporate like a puddle on a sunny pavement, of course. There is no little cloud of black hole steam drifting upward, while the universe politely pretends not to stare. Black hole evaporation is far more subtle. It comes from the uneasy meeting of quantum physics and gravity, two ways of describing nature that work beautifully in their own territories, but become difficult to combine. Near the event horizon of a black hole, quantum fields do not behave as simple, empty nothingness. What we call empty space is not truly empty. It is full of restless quantum activity, fluctuations, possibilities, field shifting in ways that are usually invisible to us. Around a black hole, the presence of the horizon changes what can be observed from far away. The result, according to Stephen Hawking's great discovery, is that a black hole should give off a faint radiation and slowly lose mass. This radiation is incredibly weak for large black holes. A black hole with the mass of a star is far colder than the background radiation that fills the universe today. That means it currently absorbs more energy from its surroundings than it loses. A giant black hole in the centre of a galaxy is colder still. If you are waiting beside one with a thermometer, first of all, please reconsider your holiday plans, and second, you would not detect a warm glow in any ordinary sense. Black holes today are not visibly evaporating away. They are too massive, too cold, and the universe around them is still too warm. The cosmic microwave background, the fading afterglow of the early universe, still bathes all of space in a tiny amount of radiation. Stars, gas, dust, and other matter also remain. Black holes can continue to gain mass for a very long time. But the background radiation cools as the universe expands, its wavelengths stretch, its energy thins. The universe becomes colder and emptier. Eventually, after vast stretches of time, the background becomes colder than the black holes. At that point, the balance changes. A black hole no longer gains more from the surrounding universe than it loses through Hawking radiation. It begins its long decline. The word begins is almost misleading here, because nothing dramatic happens at first. The black hole does not visibly shudder, glow, or announce that it has entered retirement. It simply loses mass at a rate so tiny that for ages beyond ages the change would be almost impossible to notice. If a star could be called patient, a black hole would make the star look like a child repeatedly asking if they are there yet from the back seat of the cosmic car. The smaller a black hole becomes, the warmer it gets, and the more strongly it radiates. This creates a strange pattern. Large black holes evaporate very slowly. Small black holes evaporate faster. As a black hole loses mass, its evaporation gradually accelerates. For most of its life, it barely changes. Then, near the end, the process becomes much quicker. This does not mean that a giant black hole spends half its life fading gently and half its life putting on a fireworks show. Almost all of the time is spent in the quiet stage. The ending, compared with the full lifetime, is brief. A black hole can wait through almost inconceivable spans, then finish in a final release of energy when it has become very small. The exact nature of that final moment is still uncertain, because it involves physics at extreme scales where our current theories are incomplete. We can describe much of the evaporation process, but as a black hole shrinks toward its last tiny size, quantum gravity becomes important. That is the missing theory scientists are still seeking, the theory that would join the curved spacetime of general relativity with the probabilities and fields of quantum mechanics. Without it, the final instant of black hole evaporation remains partly hidden. There may be a burst of high-energy particles. There may be a remnant left behind. There may be something stranger that our current ideas do not yet capture. The universe, in other words, keeps a few cards under the table, which is rude but very on brand. Still, the broad picture is powerful. Black holes are not eternal prisons. They're extraordinarily long-lived stores of mass and energy. Matter falls in, becomes hidden behind the horizon, and for times so vast they dwarf every stellar lifetime, the black hole simply persists. Then, through Hawking radiation, it gradually gives energy back to the universe. Not in the form of the objects that fell in. A swallowed planet does not come back as a planet. A star does not emerge again, slightly embarrassed but otherwise intact. The release is thermal, spread out, degraded, stripped of the original familiar structure. The black hole does not restore the old universe, it leaks away into a colder one. This matters because by the black hole era, almost everything else has already faded. The last stars are gone, the last ordinary sunlight is gone. White dwarfs have cooled. Neutron stars are quiet. Planets are frozen or scattered. If protons are stable, great cold objects may remain. If protons decay, much ordinary matter may have already begun to dissolve over even longer stretches. But black holes continue, and their evaporation becomes one of the main remaining sources of change. The universe no longer glows with starbirth. It glows, if that is even the right word, with the faintest possible release from the darkest possible objects. Picture an enormous supermassive black hole, one that once sat at the centre of a galaxy filled with hundreds of billions of stars. In the earlier universe, its surroundings may have been busy. Gas spiralled inward. Stars orbited close by. Other black holes merged with it. Perhaps jets blasted from the region around it, powered by magnetic fields and falling matter. But in the far future, the galaxy has thinned. Many stars and remnants have been ejected by gravitational encounters. Others have fallen in. Gas is gone or too sparse to matter. The black hole remains almost alone, a dark mass in a vast expanding emptiness. Around it, there may be little to see. Its Hawking radiation is so faint and cold that for most of its remaining life, it would barely count as a whisper. Yet slowly, steadily, it loses energy. The time involved is difficult to speak about without using numbers, and tonight we're not going to turn this into a mathematics lesson with the comfort level of a tax form. It is enough to say that these lifetimes are fantastically longer than the current age of the universe. The oldest stars we see today are only tiny beginnings compared with the duration of black hole evaporation. A supermassive black hole can outlast the entire stellar era by a margin so large that the age of stars seems almost like a brief opening note. If the universe today is middle-aged by some cosmic measures, then the black hole evaporation era lies not in its old age but in an almost unimaginable afterward. During that afterward, the universe continues expanding. Space grows emptier. Radiation stretches to lower energies. Distances between unbound regions increase beyond contact. The concept of a shared cosmic environment becomes less and less useful. A black hole may eventually sit in a region where almost nothing else can interact with it. No bright galaxies overhead, no fresh matter arriving, no nearby stars. Just the black hole and the faint structure of space with quantum fields doing their quiet work. The loneliness of such an object is hard to picture because we're used to a universe where everything belongs to some environment. Stars live in galaxies. Planets orbit stars. Moons orbit planets. Even dust belongs to clouds. But the very late universe may contain objects that are, for all practical purposes, alone. And yet even alone, the black hole is not static. Its mass decreases. Its horizon shrinks. Its temperature rises. At first, the rise is almost meaningless, like warming a frozen ocean by one thought. But as the black hole becomes smaller, the change becomes more noticeable. The radiation shifts toward higher energies. The rate of mass loss increases. Near the end, the black hole's long silence gives way to something more intense. It may release a burst of particles and radiation, a final flare after a lifetime of darkness. For a small black hole, the end is comparatively quick. For the enormous ones, the wait before that ending is so long that language mostly waves politely and wanders off for a nap. If many black holes exist across the late universe, they do not all evaporate together. Smaller ones disappear first, larger ones remain. The universe loses them in sequence, not according to a clock they all share, but according to their masses and histories. A black hole formed from a star will vanish long before a giant one formed at the centre of a galaxy. A supermassive black hole that grew through mergers may survive after countless smaller black holes have already evaporated. The last black holes to disappear would likely be the largest ones, the great central remnants of ancient galaxies, or perhaps even larger objects produced by long cosmic histories. Their final radiation may be among the last notable events in the universe. Notable, however, is a word that assumes someone or something is there to notice. By then, observers may be impossible. The conditions needed for life and consciousness, at least as we understand them, depend on organised energy flows. In the black hole evaporation era, usable energy is extraordinarily scarce and spread thin. A very advanced civilization might, in theory, try to survive by using black holes as power sources, stretching its activities across vast times, slowing its thinking, storing information in extremely efficient ways, and harvesting whatever energy remains. Such ideas have been explored in speculative physics, because once you ask how long life could persist, black holes become impossible to ignore. They are the longest-lasting batteries the universe naturally provides. But even a battery eventually drains. The question is not whether energy can be found, but whether it can be used in a way that supports organised processes indefinitely. In a universe headed toward maximum dilution and equilibrium, the answer seems likely to be no. That does not mean the thought is pointless. It teaches us something about what life requires. Life is not just matter arranged cleverly. It is matter using energy to maintain order, repair itself, process information, and act. A frozen library contains information, but it does not think unless there is energy to read, update, and respond. A brain is not just a pattern of atoms, it is an ongoing activity. A civilization is not just buildings and records, it is metabolism, communication, computation, maintenance, and warmth. As the universe ages, the raw materials may remain for a long time, but the energy gradients that make activity possible become harder to find. Black holes, for a while, are among the last places where those gradients might exist. The evaporation of black holes also raises a famous question about information. In ordinary physics, information about the state of a system is not supposed to be simply destroyed. It may become scrambled beyond practical recovery, like a diary shredded, burned, scattered into the wind, and then mixed into soup for reasons no one can justify. But in principle, the underlying information should still be part of the physical world. Black holes challenge this idea. If matter falls in and the black hole later evaporates into featureless thermal radiation, what happens to the information about what fell in? Is it lost? Is it somehow encoded in the radiation? Does it remain in subtle correlations? This is the black hole information problem, one of the great puzzles at the edge of modern physics. Scientists have made much progress in thinking about this, and many now suspect that information is not truly destroyed, but exactly how it is preserved and recovered remains a deep subject. For our far future story, the important point is that black hole evaporation is not just a clean-up process. It touches the foundations of what reality keeps and what it forgets. When the final black holes evaporate, the universe is not merely losing objects, it is undergoing the last great transformation of stored structure into radiation. The old contents of galaxies, once shining as stars and orbiting as planets, may have passed through horizons and emerged only as deeply scrambled traces in a thin bath of particles. Whether that counts as memory or erasure depends on physics we are still working to understand. There is a quiet sadness in this, but also a kind of elegance. The universe begins, in our current understanding, in a hot, dense state where energy is everywhere. It expands, cools, forms atoms, gathers stars, builds galaxies, creates heavy elements, makes planets, allows life, produces black holes, then slowly returns energy to a spread-out state. The details are not a perfect circle. The late universe is not the early universe again. It is colder, larger, more diluted, and far less capable of building complexity. But there is a broad movement from concentrated activity to dispersed calm. Black hole evaporation is one of the last steps in that movement, the final emptying of the deepest wells. As black holes shrink away, the universe loses its last major landmarks. A star is a landmark because it shines. A galaxy is a landmark because it contains stars. A black hole is a landmark because it bends space-time and gathers mass. After the black holes are gone, what remains is harder to picture. There may be photons, neutrinos, gravitons if they exist as expected, electrons and positrons depending on the fate of matter and other low-energy particles moving through an enormous expanding space. If protons have decayed, ordinary atoms are mostly gone. If protons are stable, there may still be cold remnants, but black holes will no longer provide the great gravitational anchors they once did. The universe becomes less structured, less eventful, less capable of surprising itself. One might ask whether the evaporation of everything means that literally everything vanishes. The answer depends on what we include in everything. Black holes evaporate. Matter may decay if protons are unstable. Radiation remains, stretched thinner and thinner. Space remains, as far as our models describe it. Quantum fields remain. The vacuum itself remains, unless it changes through some deeper process. So the universe after evaporation is not necessarily nothing. It is not an empty stage removed from existence. It is more like a stage with almost no actors left, the lights dimmed beyond usefulness, and the script reduced to the slow drift of faint particles across distances too large to make ordinary sense. This is why the phrase "the end of the universe" can mislead us. The universe may not end by becoming nothing. It may end, in the practical sense, by becoming unable to do much. No stars, no planets with sunlight, no galaxies as glowing structures, no black holes, no concentrated reservoirs of energy, no natural cycles rich enough to support complexity. Existence continues, but activity fades. Time may still be part of the description, but without events, without clocks, without changing structures, it becomes a thinner idea. If nothing meaningful changes, how would one distinguish one moment from another? Physics can still describe a state, but experience requires difference. The long evaporation of black holes carries us toward this question gently, because it shows that even the most durable objects are processes, not permanent fixtures. A black hole is not a final full stop. It is a comma stretched across an absurd length of time. It delays the dispersal of energy, then joins it. It takes the remains of stars and matter and holds them behind a horizon, then slowly returns them in a form that no longer resembles what entered. If stars are the universe's bright speech, black holes are its long silence afterward. And Hawking radiation is the faint exhale that proves even silence can change. The final black hole, if there is such a meaningful thing, would mark one of the last great transitions in cosmic history. For an almost endless darkness it would have persisted, larger than planets, perhaps larger in mass than entire ancient star systems, though with no surface, no glow, and no sound. Then its horizon would shrink, its radiation would grow warmer, the process would accelerate. In the final moments, the remaining mass would be released into particles and radiation, spreading outward into a universe already too large and cold to gather that energy into anything grand. No new star would form from it. No bright galaxy would awaken. The release would be real, but it would not be a rebirth in any ordinary sense. It would be the universe settling further into dilution. and after that attention turns from the objects that gravity made to the particles themselves. Stars have faded, black holes have evaporated, the great structures have given way. What remains depends on whether the building blocks of matter are truly stable, or whether over even longer ages they too can change into lighter things, radiation, and faint traces. The question becomes smaller in scale but no less profound. Not what happens to galaxies, or stars or black holes, but what happens to the atoms, the protons, the particles that once made planets, oceans, hands, and sleeping minds. The universe has grown quiet on the larger scales, and now the story begins to move inward, toward matter itself, and the possibility that even the pieces from which everything familiar is built may not remember their shapes forever. At this point in the far future, the universe has become almost unimaginably empty by the standards of our bright age. The stars have spent their fuel, the last red dwarfs have faded, black holes, after reigning over the darkness for longer than any star could have dreamed of lasting, have slowly given themselves away as faint radiation. The great structures that once made the cosmos recognizable have thinned into memory. Galaxies no longer shine as cities of suns. Nebulae no longer glow as nurseries of light. Planets, if they remain, are cold bodies moving through darkness, or fragments scattered by old gravitational encounters. It would be tempting to think the story has become simple now. Everything large has gone quiet, so perhaps what remains can simply sit there forever, unchanged, like dust in a locked attic. But physics has a way of looking into the attic and asking whether the dust itself is truly permanent. Matter feels solid to us because our lives are short and our senses are built for the middle-sized world. A table holds a cup. A stone rests in a garden. A mountain stands for ages and seems to embody permanence. Even our own bodies, changing constantly in a biological sense, are made from atoms that feel like reliable ingredients. Carbon, oxygen, hydrogen, nitrogen, iron, calcium. All the familiar pieces of chemistry seem dependable. They form water, rock, bone, air, wood, blood, leaves, oceans, and the small crumb you may have found in your sleeve and decided not to investigate too closely. The world appears to be made of things, and things appear to last unless something obvious breaks them. But at the deepest levels, matter is not as still as it appears. Atoms are not tiny solid beads. They are structured systems of particles and fields. Their electrons occupy quantum states. Their nuclei are made of protons and neutrons. Those protons and neutrons are made of quarks bound together by the strong nuclear force. What feels like solidity is really the result of forces, rules, probabilities, and the resistance of quantum particles to being pressed into the same state. Ordinary matter is less like a pile of bricks, and more like a carefully maintained agreement among fields. It holds together extremely well under normal conditions, which is lucky, because breakfast would be difficult if toast kept reconsidering its atomic commitments. Yet when we ask about the farthest future, extremely well is not the same as forever. One of the great open questions in physics is whether the proton is truly stable. Protons are found in the nuclei of atoms, and hydrogen, the simplest atom, is just a proton with an electron. If protons last forever, then ordinary matter can persist in some form for inconceivably long times. Even after stars and black holes are gone, if protons decay, then matter itself has a hidden lifetime. Not a lifetime short enough to matter in daily life, or in the life of a star, or even in the lifetime of the universe so far, but a lifetime that becomes important in the deep future. Experiments have searched for proton decay and have not found it. That means if it happens, it must be fantastically rare. A single proton in a glass of water is not sitting there looking nervous. It is, for all practical purposes, stable. But the far future is not practical. It is where almost impossible processes are given enough time to become relevant. Some theories that try to unify the forces of nature suggest that protons might eventually decay into lighter particles. These ideas are not confirmed, but they are taken seriously enough that scientists have built enormous detectors to watch for the faint signs of such an event. The challenge is that proton decay, if it happens, is so rare that you cannot watch one proton and hope to catch it before bedtime. You need vast amounts of matter and great patience. The fact that no decay has been seen tells us that protons, if unstable, live for spans of time so huge that even cosmic history so far is only the first page of a very long book. If protons do decay, the distant universe changes in a profound way. Cold planets, black dwarfs, asteroids, dust, and ordinary atomic matter would not remain as silent relics forever. Their nuclei would gradually break down. The process would be incredibly slow, not like a stone crumbling in weather, not like rust spreading across metal, but like the rarest possible internal forgetting. One particle here, another there. Ages pass between meaningful changes. From the outside, a cold planet might appear unchanged for unimaginable durations, but deep inside, proton by proton, its matter would be transforming into lighter particles and radiation. Over enough time, the planet would lose mass, its atoms would fail, its structure would weaken. What had once been rock, ice, metal, or frozen atmosphere would dissolve into a thin drift of particles. The phrase matter may forget itself is not physics terminology, but it captures the feeling. Matter remembers its identity through stability. A proton remains a proton. A carbon nucleus remains carbon. A crystal keeps its lattice. A planet keeps its shape because its atoms remain atoms, and its gravity holds them together. But if the particles at the foundation are not eternal, then that memory has limits. The forms that made stars, worlds, oceans, and bodies would not be preserved indefinitely. They would become radiation and lighter particles, spreading into the already enormous universe. The old shapes would not be smashed by a dramatic collision. They would fade through the quiet failure of their ingredients to remain themselves. This would be a very different kind of ending from the death of a star. A star dies because it spends fuel and gravity changes the balance inside it. A black hole evaporates because quantum effects near its horizon allow it to lose energy. Proton decay, if real, is more intimate. It says that the matter making up a stone is not merely cold and inactive, but subject to a hidden instability at the particle level. No furnace is needed, no impact is needed, no nearby star is needed. Time itself, along with the laws of particle physics, is enough. The stone can sit in perfect darkness, untouched, and still eventually cease to be a stone. Of course, we do not know that this happens. That uncertainty matters. The far future has two broad paths here. In one, protons decay and ordinary matter gradually dissolves. In the other, protons are stable and matter can remain for far longer, though not necessarily in familiar forms. Science is often most interesting when it refuses to give a single clean answer before the evidence is ready. The honest picture is that we have not yet seen proton decay, so we cannot claim it as fact. But we can explore what it would mean, because the question touches the fate of almost everything made of atoms. Suppose protons do decay. Then after black holes evaporate, or perhaps alongside that long era depending on timescales, the remaining matter slowly breaks down. White dwarfs that cooled into black dwarfs would be affected. These cold stellar cores, once made of dense atomic nuclei and electrons, would not remain as eternal dark spheres. Their material would decay from within. Planets orbiting dead stars would do the same. Rogue planets drifting between old galaxies would slowly lose their substance. Comets, frozen moons, metal-rich asteroids, grains of dust, all would share the same quiet fate. The universe would become less and less a place of objects and more a place of particles and radiation. There is something almost tidy about that, though not tidy in the way a human room becomes tidy after someone finally deals with a laundry chair. The universe would be simplifying. Complex structures would give way to simpler products. Chemistry would become impossible once atoms are no longer stable. Molecules would have no lasting future. Crystals would lose their lattices. Ice would not remain ice. Rock would not remain rock. Matter would not support landscapes, interiors, surfaces, or climates. The idea of a world would become obsolete because worlds require stable material. A planet is a long-term arrangement of matter under gravity. Remove the stability of that matter, and the arrangement cannot last. If protons decay, then even the distinction between different chemical elements eventually loses importance. The periodic table, which organizes the substances of ordinary life, belongs to the era of stable atoms. It is one of the great maps of the middle universe, the universe of stars and planets, and laboratories and kitchens. In the deep future, that map may no longer describe what exists. There would be no oxygen to breathe, no carbon to build cells, no iron to hold a core, no silicon to make rock, no calcium in bones, no gold hidden in old crusts, no salt in ancient oceans. The elements would have been temporary chapters in the behaviour of particles, useful, beautiful and essential to everything we know, but not permanent. If protons do not decay, the story becomes stranger in another way. Cold matter remains, but over enormous timescales it can still change through rare quantum processes. Quantum mechanics allows particles and systems to do things that would be impossible in ordinary classical thinking, though often with probabilities so tiny that they never matter in everyday life. Given enough time, cold objects may gradually rearrange toward more stable forms. One speculative idea is that matter in cold stellar remnants could slowly transform through quantum tunneling processes, perhaps tending toward iron, one of the most stable nuclear configurations. People sometimes call the hypothetical end products iron stars. These would not be stars in the shining sense. They would be cold, dark, dense objects made largely of iron-like material, formed not by burning, but by unbelievably slow quantum rearrangement. This idea depends on protons being stable. If protons decay, iron stars never get their chance. Matter dissolves before such slow transformations can dominate. If protons are stable, then the universe may contain cold, dark remnants that change so slowly that even the black hole era seems energetic by comparison. The transformation of matter would not produce warm starlight or living worlds. It would be a deep, silent adjustment toward lower energy states. The universe would be filled with objects that are still objects, but no longer active in any ordinary sense. They would not shine. They would not form new chemistry. They would not host weather. They would simply persist, occasionally altered by rare events that require time beyond imagination. There are also gravitational processes to consider. Even if matter stays stable, cold remnants are not guaranteed to remain safely apart forever. Over huge times, gravitational encounters can scatter objects into space, or send them toward black holes, though after black holes evaporate, that route closes. In systems where objects remain bound, gravitational radiation can slowly drain orbital energy, causing pairs of dense remnants to spiral inward and merge. These mergers could release bursts of energy, perhaps creating brief events in an otherwise dark universe. But as expansion separates unbound regions and as local systems thin out, such encounters become rarer. The remaining matter, whether stable or decaying, becomes increasingly isolated. If atoms somehow remain forever, one might imagine that the universe would at least keep a kind of fossil record. Frozen planets, dead stars, cold rocks, a museum without lights. But a museum is meaningful only if something can visit, read, compare, and remember. In a universe without usable energy gradients, without stars, without black holes as power sources, and without active processes rich enough to sustain observers, the difference between a preserved fossil and an unreadable arrangement of particles becomes less comforting. The structure may remain, but the ability to use or experience that structure may be gone. A book sealed in ice on a planet without light is still a book in one sense, but without readers, Language becomes a pattern waiting for a mind that will not come. This brings us back to what matter meant during the Bright Age. Matter was never just stuff, it was possibility. Hydrogen gathered into stars. Stars made heavier elements. Heavy elements formed planets. Planets allowed chemistry. Chemistry allowed life. Life arranged matter into memory, movement, hunger, sleep, and curiosity. And matter became forests, coral reefs, feathers, eyes, hands, and minds. It became instruments that measured starlight and words spoken softly into microphones. It became someone asking what happens after the end of the universe. In the far future, matter may lose that ability not because the particles become worthless, but because the conditions that allow complexity to renew itself disappear. The decay or persistence of matter also affects the meaning of darkness. A dark universe full of cold planets is different from a dark universe with no atoms left. In the first, there are still relics, even if they are unreachable and inactive. In the second, the relics themselves have dissolved. One is a graveyard. The other is more like the slow fading of the graveyard into mist. Both are quiet, but they are not the same kind of quiet. This is why the question of proton stability matters so much to cosmic destiny. It decides whether the far future contains ancient objects or mostly the products of their decay. Even if matter decays, not everything becomes nothing. Decay products would remain, radiation would remain. Very light particles might drift through the expanding universe. Electrons and their antimatter partners, positrons, might exist depending on the decay processes. Neutrinos would continue to stream through space. Photons would be stretched to longer and longer wavelengths. The universe would be thin, cold, and nearly featureless, but not absolute nothingness. Physics is usually not in the business of making true nothing. It rearranges what exists. It changes forms, spreads energy, dissolves structure, lowers the ability of systems to do work. The end of matter as we know it would not be a magic disappearance. It would be transformation into a state where the old categories no longer apply. There is a gentle lesson in that. The things we call permanent are often just long-lived compared with us. A mountain seems eternal because it outlasts generations, but plate tectonics, erosion, and weather will eventually change it. A star seems ancient, but it burns through fuel. A black hole seems final, but it evaporates. A proton may seem unbreakable, but perhaps it too has a future. We live in a universe where endurance comes in layers. Human moments are brief. Biological species last longer, planets longer still, stars longer than planets in many cases, black holes longer than stars, particles perhaps longest of all, unless even they change. The far future strips permanence away one layer at a time, and yet this does not make the present fragile in a useless way. It makes it active. The matter in your body was not always yours. It passed through stars, gas clouds, planets, food, air, and water. It is temporarily arranged into you, which is a very unusual and interesting thing for matter to be doing. Most matter is not listening to thoughts about cosmology while settling towards sleep. Most matter is not aware of anything. For a while, some of it becomes alive. For a shorter while, some of it becomes conscious. For an even more specific while, some of it wonders about proton decay in a calm voice at night. That temporary arrangement is not less remarkable because it will not last forever. It is remarkable because the universe found a way to do it at all. So when we imagine matter forgetting itself, we are not imagining failure. We are following the same thread we have followed all along. Stars forget their fuel and become remnants. Black holes forget their mass into radiation. Matter may forget its particles into simpler forms. Structure gives way to spread. Complexity becomes rarity, then memory, then perhaps not even memory in any active sense. The universe does not erase itself in anger. It relaxes through the consequences of its own laws. Every stable thing is stable under certain conditions and across certain times. The deep future asks what happens when the conditions are gone and the times are unlimited. Somewhere in that future, if protons decay, the last cold planet may slowly lose its final atoms, not in a flash, not with an explosion. No sky would brighten, no witness would hear a crack. The planet would have been dark for ages, perhaps drifting alone since the death of its star, its mountains frozen harder than any winter Earth has known, its old surface marked by impacts from times when there were still things nearby to collide with it. Then, across spans beyond counting, the particles inside it would transform. The world would thin, its gravity would weaken, its structure would fail. Eventually it would no longer deserve the name planet. It would become a faint contribution to the background of particles moving through space. The place where landscapes once could have been would have no surface, no inside, no outside, no weather, no waiting. If protons are stable, the last cold objects may remain instead, dark and silent, altered only by rare quantum changes and gravitational accidents. That future is less dissolved but not truly alive. Matter remembers its identity, but there is almost nothing left for it to do. It is the difference between a sleeping stone and a vanished stone, and from the viewpoint of experience, both are deep forms of silence. Still, physics cares about the difference, and so do we, because asking what remains is part of how the universe examines itself through us. By now, the cosmic story has moved far beyond ordinary endings. The fading of stars was an ending we could picture. The evaporation of black holes was stranger, but still centered on objects with gravity and horizons. The possible decay of matter reaches into the foundation of everything familiar. It asks whether the ingredients of atoms are final or temporary, whether the periodic table is a permanent feature of reality or a long-lived phase, whether the cold remains of worlds persist forever or quietly dissolve. However the answer falls, the direction of the far future remains similar. The universe becomes less able to build, less able to shine, less able to concentrate energy into useful forms. Matter either fades away or sits in darkness with almost nothing left to stir it, and the next question becomes the broadest and stillest one of all. What happens when energy is spread so thinly and differences have become so small that the universe approaches a state where nothing meaningful is left to happen? By the time matter itself has either dissolved into lighter particles or settled into cold, stubborn remnants, the universe has become almost impossible to compare with anything familiar. It is no longer a place of sunrise and shadow. It is no longer a place where clouds of gas collapse into stars, or where galaxies glow like cities seen from far away. The bright engines have shut down. The great black holes have slowly leaked away. The old planets, if any remain, are frozen, scattered, or reduced by particle decay into faint radiation and drifting fragments. What remains is not nothing, but it is getting close to the most inactive kind of something physics can describe. The universe has not necessarily ended by vanishing. It has ended in the sense that it has almost run out of ways to make events happen. This is the idea often called heat death, and the name is a little misleading at first. It sounds as if the universe becomes unbearably hot, as though everything ends in a cosmic oven, which is not a very restful image and would also be terrible for houseplants. Heat death does not mean the universe is filled with heat in the everyday sense. It means that energy has become so spread out, so diluted and so evenly distributed that there are no useful differences left to drive change. A hot cup of tea cools because heat flows from the tea into the cooler room. A battery powers a device because there is stored chemical energy that can move through a circuit. A waterfall can turn a wheel because water is higher in one place and lower in another. A star shines because matter is compressed and hot in its core while space around it is colder. Useful activity comes from imbalance. It comes from differences. Heat death is what happens when those differences fade away. The universe today is full of differences. Stars are hotter than the space around them. Galaxies are denser than the voids between them. Planets have surfaces, interiors, atmospheres, oceans, and winds. Living bodies maintain strong boundaries between inside and outside. Cells keep certain chemicals in one place and others in another. Brains work by maintaining and changing tiny electrical and chemical differences across membranes. Every thought, every heartbeat, every breath, every little moment of irritation when a blanket corner refuses to behave depends on the universe having usable gradients of energy. The far future removes those gradients one by one. Stars spend their fuel, matter spreads, radiation stretches, black holes evaporate, particles drift farther apart. The structures that once kept energy concentrated slowly give way. Entropy is the word physicists use when talking about this broad direction. It is often described as disorder, but that can be a little too casual. A messy room has more disorder than a tidy room, but entropy is not just cosmic untidiness. It's connected to the number of ways a system can be arranged while still looking the same on a large scale. A neat stack of papers has fewer possible arrangements than a floor covered in scattered papers. The scattered version can be made in many more ways. Natural processes tend to move towards states that are more likely, and those are usually states where energy is more spread out. This is why the tea cools instead of gathering warmth back from the air and politely reheating itself. The cooled tea and slightly warmed room are a more probable arrangement than all the heat being concentrated back in the cup. The universe follows this kind of logic on scales far beyond kitchens. In the early universe, matter and energy were arranged in a way that allowed gravity to build structure. Gas gathered into stars. Stars created heavy elements. Heavy elements formed planets. Energy flowed from hot stars into cold space. For billions of years, and then for vastly longer during the age of faint red stars, those differences allowed complexity to exist. Heat death is not a sudden rule that appears at the end. It is the long-term result of the same rule that has been operating all along. Energy spreads. Entropy rises. The universe becomes less able to produce organized activity because the concentrated sources that feed activity are gradually used up. This does not mean the universe becomes perfectly uniform in a simple visual sense. Depending on the fate of matter, there may be particles scattered across space, or cold remnants in regions that were once gravitationally bound, or extremely faint radiation moving through expanding distances. If dark energy continues to behave as it appears to behave today, the expansion of the universe keeps separating regions that are not bound together. Each region becomes more isolated. Radiation stretches to longer wavelengths and lower energies. The cosmic background becomes colder and fainter. Any remaining particles become more widely separated. In practical terms, the universe becomes a place where the chance of interactions falls toward almost nothing. A particle may travel through emptiness without meeting anything else, for spans of time that make all previous cosmic history seem brief. There is a difference between emptiness and equilibrium, though in the far future they begin to feel related. Emptiness means there is very little there. Equilibrium means what is there has no usable imbalance left. A sealed room eventually reaches a nearly even temperature if there are no heat sources or cold spots. Once everything is the same temperature, a heat engine cannot run because there is no direction for heat to flow usefully. The heat has not disappeared. It is just no longer available to do work. In the cosmic case, the energy is not simply spread evenly inside a small box. Space itself keeps expanding, and the contents become diluted, but the essential point remains. Without strong differences, there is no fuel for change of the kind that builds stars, supports life, or powers machines. This is why heat death is sometimes described as maximum entropy. It is not allowed destruction, but a final exhaustion of usable structure. A universe in this condition may still contain radiation. It may still contain particles. It may still have quantum fields. But it no longer has the kinds of organized energy flows that make events interesting at large scales. No star can ignite because there is no cold dense gas left in the right conditions. No planet can be warmed by sunlight because there are no stars. No black hole can serve as a long-lasting energy source because the black holes have evaporated. No chemistry can continue in the old way if atoms have decayed, and even if some atoms remain, the surrounding environment is too cold, thin, and inactive to support complex cycles. The universe becomes a clock with no moving hands, or perhaps a clock whose hands still exist but have no reason to turn. The word stillness here should be handled carefully. On the smaller scales, quantum fields are never simply dead in a classical sense. There may be fluctuations. There may be rare events allowed by quantum mechanics. Empty space is not a blank nothingness like an empty cardboard box. It is a physical state with properties. But for the purposes of stars, planets, life, memory, and ordinary events, the stillness is real enough. It is the stillness of no available work, the stillness of no fires left to burn, the stillness of differences flattened by time. If a universe can become tired, this is the closest physics comes to describing it, though of course the universe is not actually tired. Tiredness belongs to bodies with nerves, muscles, and regrettable sleep schedules. The universe is simply following its laws. It may help to think about a simple object like a womb clock. When it is wound, it contains stored energy. The spring can drive gears. The gears move hands. The hands mark time. Eventually the spring unwinds. The clock still exists, but it no longer does the thing that made it useful as a clock. You could keep it on a shelf. You could admire its case. But unless someone winds it again, its internal ability to produce motion has been spent. The universe is not exactly a clock, but heat death has a similar feeling. The parts may not all vanish, but the ability to power large-scale organized change has drained away. There is no outside hand to rewind the cosmic spring. This last point matters. In ordinary life, systems can become ordered again because they are not truly closed. A person can tidy a room by using energy from food. The food came from plants, and the plants use sunlight. The sunlight came from nuclear fusion in the sun. The sun formed from gas gathered by gravity. The local decrease in disorder inside the room is paid for by a larger increase elsewhere. Living things create and maintain order by exporting disorder into their surroundings. This is not cheating. It is exactly how life works. But the universe as a whole, as far as we can tell, has no outside environment from which it can borrow fresh low entropy energy. If the total supply of usable differences is exhausted, there is no larger cosmic kitchen where someone is preparing another pot of energy soup. That is why heat death feels so final. It is not the end of one system within a larger world. It is the decline of the conditions that allow systems to renew themselves at all. A dead star can leave material for another star if there is still gas, gravity, and time. A collapsed ecosystem on a planet might recover if sunlight continues, and chemistry remains active. A civilization might rebuild after disaster if resources and energy flows remain, but in heat death, the background conditions for renewal are gone. There is no fresh star formation, no concentrated fuel, no active reservoirs waiting nearby. The universe is not destroyed in a single catastrophe. It becomes unable to restart ordinary complexity. The role of dark energy deepens the stillness. The expansion of the universe appears to be accelerating, driven by something we call dark energy, because we do not yet know its deeper nature. If it remains constant in the simplest way, then distant regions of the universe continue to move beyond one another's reach. Over time, each gravitationally bound region becomes isolated behind its own horizon. This horizon is not a wall made of matter. It is a limit set by expansion and the speed at which signals can travel. Events beyond it can no longer influence the observer. In the far future, the observable environment of any remaining location becomes smaller in a meaningful sense, not because nearby space shrinks, but because the rest of the universe becomes causally unreachable. Heat death is therefore not only a thinning out of energy, it is also a loss of contact. That loss of contact makes the future even less able to organize itself. To build structure, matter and energy must interact. Gravity needs time to gather matter. Radiation needs objects to strike. Chemistry needs atoms close enough to bond. Life needs cycles. Computation needs controlled physical processes, but expansion pulls the large-scale universe apart, and the remaining contents grow sparse. Even if somewhere there is a particle, and somewhere else there is another, they may never meet. They may not even share a future-like cone in any useful way. The universe becomes a collection of isolated traces rather than a connected arena of activity. It is difficult to make a story when the characters can no longer reach one another. The absence of observers is not required for heat death, but it follows naturally from what heat death removes. Observers need energy and memory. Memory requires physical states that can be maintained and distinguished. Thought requires change. A mind is not a static object. It is a process, a controlled flow of signals, repairs, comparisons, and updates. In a heat-death universe, processes like that become impossible because there are no usable gradients to drive them. A perfectly still mind would not be a mind experiencing quiet. It would simply not be experiencing. Sleep is peaceful because the body continues its hidden work. Breathing continues, cells repair, the brain cycles through states. Heat death is not sleep. It is closer to the absence of any system capable of sleeping. This is important because people sometimes imagine the final stillness as if someone is there, floating in darkness and feeling lonely. But loneliness requires a mind. Darkness requires eyes or instruments. Silence requires ears or detectors. In heat death, there may be no one to feel the absence. The universe does not become sad. It becomes inactive. The emotional weight belongs to us because we are alive now, in the active era, trying to picture a future without activity. We bring our human sense of endings to a condition that may not contain any experience at all. That does not make the idea meaningless. It only reminds us that our imagination is built for rooms, skies, clocks, and bodies, not for a nearly empty, expanding cosmos after the last sources of work are gone. There is also a strange comfort in this. Heat death is not a monster waiting at the edge of time. It is not a disaster approaching in any humanly relevant future. It lies so far beyond the lives of stars, worlds, and black holes that the numbers would do very little for our intuition. The sun will change long before then. Earth's habitability has its own limits long before the last stars. Galaxies will merge. Red dwarfs will burn for vast ages. Black holes will persist for longer still. Heat death is not tomorrow's problem, or civilization's problem, or even a problem in the usual sense. It is the asymptotic direction of the universe if the known trends continue. It is not a deadline on a calendar. It is the long fading of the possibility of deadlines. Still, it is worth asking what remains meaningful in a universe headed this way. Some people hear about heat death and feel that it makes everything pointless. If all structures eventually fade, why do anything? But that question quietly assumes that meaning requires permanence. In ordinary life, we rarely behave that way. A meal matters even though it ends. A song matters even though its last note fades. A conversation can be valuable even though the sound waves vanish almost immediately. A person's kindness matters even though the universe will not preserve a glowing plaque about it for eternity. Meaning is not the same as endless duration. It belongs to relationships, experiences, effects, and awareness while they exist. The far future does not erase the reality of the present. It simply tells us that the present is part of a changing universe, not an escape from one. In fact, heat death can make the present feel more specific. We live in a rare kind of cosmic weather. There are stars overhead. There are temperature differences, chemical flows, planetary cycles, and enough order for life to maintain itself. There is free energy pouring from the sun every day. There are galaxies still visible beyond our own. There are records of the early universe still detectable. There are atoms stable long enough to form bodies and brains. We live in an era when the universe is not only active, but readable. It can be studied. It can be measured. It can be wondered about. The final stillness has not arrived. The cosmic room is still warm enough for thought. This does not mean we should turn the far future into a comforting story that ignores its severity. Heat death is severe. It is the end of stars, the end of ordinary life, the end of natural complexity, the end of all processes that depend on usable energy. It is not a happy ending in any familiar sense. But it is also not a violent ending. It is quiet. It is lawful. It is the continuation of tendencies already visible in small things. Tea cools, batteries drain, fires burn out, stars shine by spending fuel, black holes evaporate, energy spreads. The universe is not doing something alien at the end. It is doing what it has always done, only with no new concentrated sources left to delay the outcome. The phrase perfect stillness is therefore not about absolute lack of anything. It is about the disappearance of meaningful imbalance. Imagine a vast ocean with no waves, no currents, no wind, no temperature differences, no shores, and no creatures moving through it. Water might still exist, but the ocean would have no weather, no tides, no drama. Heat death is like that, though even the ocean image gives too much substance and too much nearness. The late universe is thinner, colder, and more separated than any ocean. Its stillness is not smooth blue water. It is a near absence of opportunities. Could anything happen after that? This question is where the far future becomes uncertain again. In a simple heat-death picture, meaningful events become vanishingly rare. But quantum physics allows for fluctuations, and cosmology leaves open questions about the nature of dark energy, the vacuum, and the deep structure of reality. There may be incredibly rare fluctuations in a heat-death universe. There may be changes in the vacuum state. There may be processes we do not yet understand because our current theories are incomplete. Some speculative ideas suggest that new universes could arise from conditions that look empty to us, or that cosmic inflation could produce regions of new expansion. Others suggest that the vacuum itself might not be absolutely stable. These possibilities are not established facts, but they keep the story from becoming a simple full stop. Before we wander into those possibilities, it is useful to stay a little longer with the stillness itself. Heat death is the most conservative end in many current models because it follows from known thermodynamic behavior and the observed accelerated expansion. It does not require a sudden tear in space, a collapse of everything back inward, or a dramatic new law. It is the outcome of ordinary processes given extraordinary time. It is the universe becoming old in the deepest physical sense, not old like a person, because people gather memories and meanings, not old like a tree, because trees grow, repair and respond, old like a system whose usable differences have been spent. And yet even this old universe may not be the last word, because the question what happens after the end of the universe depends on what we mean by after. If time continues but nothing changes, after becomes a strange word. If the vacuum can fluctuate, after may contain rare surprises. If a new region of spacetime can bud off from an old one, after may not be inside our universe in the usual sense at all. If the laws of physics allow recurrence across unimaginable durations, then even stillness may have exceptions, though whether those exceptions can be meaningful is deeply debated. The perfect stillness is the end of the familiar story, but not necessarily the end of every possible question. Once the universe has cooled into near inactivity, the mind naturally turns to the last remaining uncertainty, whether darkness is only darkness, or whether the deepest emptiness in physics can still contain the seed of something that looks, from the inside, like a beginning. Once we've imagined the universe in heat death stretched thin and quiet, with no stars left to burn and no black holes left to evaporate, it feels natural to think we've reached the last page of the story. Not a dramatic last page, perhaps, not one with thunder and trumpets, but a page where the ink has faded until there is almost nothing left to read. Energy has spread out. Matter has either decayed or settled into cold isolation, The great engines of change are gone. If the universe were a house, every lamp would be off, every fire would be cold, and even the old floorboards would have stopped creaking. But physics is very good at making us hesitate just when we think we have reached a full stop. Because even in the deepest stillness we can imagine, there remains a question. Is that truly the end, or can a new beginning somehow arise from what looks like ashes? The word ashes is only a metaphor here, of course. By the time we are talking about the farthest future, there may be no ashes in the ordinary sense. Ashes belong to fires, to chemistry, to oxygen, to wood, to stars that made carbon and planets that made forests. The future after heat death may not contain anything as familiar as dust on a hearth. It may contain thin radiation, lonely particles, quantum fields, and the strange condition we call vacuum. But the metaphor is useful because ashes suggest the remains of something that once burned brightly. Our universe certainly has burned brightly. It has made stars, galaxies, planets, lightning, cells, eyes, minds, and small conversations under blankets. If all of that fades, the question becomes whether the remains are only remains, or whether under some deep physical rule they might allow something new to happen. The simplest answer is that maybe nothing new happens in any meaningful way. That is the conservative picture. Heat death leaves a universe too cold, too spread out, and too close to equilibrium to build anything large and organised again. No star-forming clouds, no fresh supply of low-entropy energy, no cosmic reset button with a nice friendly label. In this view, the universe does not rise again. It continues in a state of fading activity, perhaps forever, perhaps until the very idea of time becomes almost empty because there are no events left to count. If nature follows only that path, then the end is not an explosion or a rebirth. It is a long, quiet persistence. The universe does not wake, it simply remains. But scientists have learned to be cautious with simple answers about the whole of reality. The universe has surprised us before. It surprised us by expanding. Then it surprised us by expanding faster. It surprised us with black holes, with quantum uncertainty, with the fact that empty space is not quite the plain empty, nothing our intuition expects. So although heat death is a leading possibility, physicists and cosmologists have considered other futures and deeper possibilities. Some are speculative, some are mathematical, some may never be testable in the direct way we would like, but they are not mere fantasy. They are attempts to understand what our laws, or possible future versions of our laws, might allow when pushed to the largest scales and the longest times. One idea is that the universe might be cyclic. In a cyclic picture, the cosmos does not simply begin once, expand once, and fade once. Instead, it passes through repeated phases. A universe expands, changes, perhaps empties or collapses or transforms, and then a new phase begins. The old dream of a cyclic universe often involved a big crunch, where expansion slows, stops, and reverses. Galaxies fall back toward one another, the universe contracts, temperature and density rise. Eventually everything returns to an extremely hot, dense state, perhaps followed by a new expansion, a new Big Bang. It is a dramatic picture, rather like the universe breathing in and out across eternity. Very grand, very cinematic, and probably difficult to fit into a sensible bedtime routine. The trouble is that current observations suggest the expansion of the universe is accelerating. Distant galaxies are not slowing their retreat in a way that points toward an eventual collapse, at least under the simplest interpretation. Dark energy appears to be pushing the large-scale expansion onward. If dark energy remains as it seems to be now, a big crunch becomes unlikely. The universe would not turn around and fall back in. It would keep expanding, becoming emptier and colder. That does not completely kill every cyclic idea, because some models do not require a simple collapse of the whole universe, but it does mean the old straightforward bounce, where gravity eventually pulls everything back together, is not the favoured outcome. There are more subtle bounce ideas. Some theories suggest that what we call the Big Bang may not have been an absolute beginning, but a transition from a previous state. Perhaps there was a contracting universe before ours. Instead of collapsing into a final singular point, the contraction reached an extreme density where new physics took over, causing a bounce into expansion. In that picture, our universe could be the expanding side of a previous cosmic collapse. The beginning would not be creation from nothing, but a rebound. Like a ball compressed against a surface and springing back, though with the important difference that this ball contains all of space, time, matter, radiation, and every future cup of tea. These bounce models are fascinating because they try to avoid the idea of a beginning where known physics simply breaks down. In general relativity, if we trace the universe backward using the simplest equations, we reach a state of extreme density and temperature where the theory itself signals its own limits. A true singularity is not necessarily a physical object. It may be a sign that the theory has been stretched beyond where it can work. Quantum gravity, the still unfinished theory that would combine gravity with quantum mechanics, may replace that singular beginning with something else. A bounce is one possible something else. If so, then perhaps universes can come before universes, and what feels like a beginning from inside one phase is only a transition in a larger history. But a bounce does not automatically mean our far future will create another universe. A model of the early universe may say something about what came before our expansion, while a model of the future must deal with dark energy, heat death, entropy, and expansion. A universe can have a prehistory without having an endless cycle. The past may contain a bounce while the future still ends in cold dilution. Physics does not owe us symmetry, even though we often find symmetry aesthetically pleasing and would like the universe to keep its stationary neatly matched. Another family of ideas involves inflation. Cosmic inflation is the proposal that the very early universe underwent an extremely rapid expansion, stretching tiny regions to enormous size. It helps explain why the observable universe is so smooth on large scales, why space appears close to flat, and why tiny quantum fluctuations could become the seeds of galaxies. In many versions of inflation, the process may not end everywhere at once. Some regions stop inflating and become universes like ours, while other regions continue inflating. This leads to the idea of eternal inflation, where new bubble universes keep forming within a larger inflating background. Each bubble may have its own local beginning, its own expansion, perhaps even its own physical properties. If eternal inflation is correct, then our universe may be only one region in a much larger multiverse. In that wider picture, the end of our universe would not be the end of all reality. It would be the cooling and fading of our bubble, while elsewhere other bubbles continue to form. New universes wake not from our ashes exactly, but from the same deeper inflating process that produced ours. Imagine foam, with each bubble a universe. One bubble may grow old and dark, while others appear elsewhere in the foam. From inside any one bubble, the others may be unreachable forever. Their existence would not help anyone living in a dying universe, but it would change the meaning of cosmic ending. The end would be local, not total. This idea is both thrilling and frustrating. It offers a grander setting, but it is hard to test. Other bubble universes may be beyond our observational reach. Some physicists hope there could be subtle traces, perhaps signs of collisions between bubbles in the early universe, but no confirmed evidence has shown that, so eternal inflation remains a serious but uncertain possibility. It lets us imagine creation continuing beyond our cosmic horizon, but it does not give us a simple way to prove that such creation is happening. It is a little like hearing that there may be other rooms beyond a locked wall, but all the doors are hidden, and the wall is expanding away from you, which is inconvenient architecture. There is also the possibility of baby universes. In some speculative ideas, new universes might form inside black holes, or through quantum gravitational processes that pinch off a new region of spacetime from an old one. A black hole from the outside hides whatever crosses its event horizon. From the inside, under some models, the collapse might avoid a singularity and instead lead to an expanding region, a new universe with its own space and time. If that were true, black holes could be cosmic seeds. Every large black hole might contain, beyond the reach of outside observers, the beginning of another universe. This is an astonishing thought, and it should be handled gently. It is not established science. We do not know that black holes create universes. We do not know what happens at the deepest interior of a black hole, because that is exactly where quantum gravity becomes necessary. But the idea appears in serious theoretical discussions because black holes and Big Bang-like conditions both involve extreme gravity, density, and the breakdown of familiar descriptions. If singularities are replaced by bounces or transitions, then perhaps collapse in one region can become expansion in another. From the parent universe, the baby universe may be forever hidden. It might detach causally, becoming its own cosmos. Nothing useful may travel back. No postcard arrives saying, "New universe formed successfully, weather hot, wish you were here." If new universes can form through black holes, then our universe may have produced many offspring during its active era. Massive stars formed black holes. Galaxies formed supermassive black holes. Mergers made larger ones. The cosmic family tree could be vast. There is even a speculative idea called cosmological natural selection, where universes that produce more black holes produce more baby universes, and physical laws might evolve across generations of universes in a way loosely analogous to biological selection. This is imaginative and controversial, but it shows how the question of a new universe can connect black holes, particle physics, and the values of nature's constants. It is not something we can treat as fact, but it is a fascinating example of how far the mind can go when it follows the mathematics to strange places. Another possibility lies in the nature of the vacuum itself. In physics, the vacuum is not simply empty space. It is the lowest energy state of fields, or at least what appears to be the lowest energy state available to us. But what if our vacuum is not truly the lowest possible state? What if it is only metastable, like a ball resting in a shallow dip on a hillside, stable for a long time but not absolutely stable? If there is a deeper vacuum state, then in principle a transition could occur. A tiny bubble of the lower energy vacuum might form through quantum tunneling and expand outward, changing the laws and properties of space as it goes. This is called vacuum decay. Vacuum decay is not a cozy scenario for anything inside the affected region. It would not be a gentle rebirth of stars and gardens. It would be a transformation of the ground rules of physics. Atoms as we know them might not hold together. Particles might have different masses. Forces might behave differently. From our point of view, it would be catastrophic. However, in the context of far future cosmology, vacuum transitions raise an important point. What looks like empty stable space may contain the possibility of change. A heat-death universe might not be the absolute end if the vacuum itself can transition into a new state. Whether that new state could count as a new universe, or simply a different phase of the old one, depends on the details. And those details are very much not settled. The reassuring part for tonight and for every ordinary night is that if our vacuum is metastable, it appears to be extremely long-lived. Nothing suggests that such a transition is imminent. The far future gives quantum possibilities a lot of time, but daily life does not need to include checking under the bed for vacuum decay. It is enough to know that empty space may have depth, and that the final stillness of heat death might not be completely immune to rare transformations at the level of fields. There is also a more mind-bending idea known as recurrence. In certain systems with finite energy and certain constraints, given enough time, states can return arbitrarily close to previous arrangements. This has led some people to wonder whether in an eternal universe, fluctuations might eventually recreate structures, observers, or even entire cosmic histories. But applying this idea to our expanding universe is extremely difficult and controversial. The universe is not a simple sealed box with a fixed set of particles bouncing around forever. Space expands, horizons exist, gravity complicates the accounting, quantum fields and dark energy add further puzzles. Still, recurrence-related thinking raises an unsettling possibility. If time is endless, and if certain fluctuations are allowed, then rare events may occur no matter how improbable. The issue is not whether something is merely unlikely, but whether the framework gives it infinite opportunity. This leads to strange discussions about Boltzmann brains, hypothetical observers that arise from random fluctuations in a high-entropy universe. The idea is not that such things are likely in any normal sense. It is that if a heat-death universe lasts forever, and fluctuations can produce complex structures, then a self-aware brain with false memories might be more common than ordinary observers produced by cosmic evolution. This is deeply weird and not especially bedtime-friendly unless handled carefully, perhaps with a biscuit. Physicists use this problem not because they expect lonely brains to pop out of the void like confused cosmic mushrooms, but because it tests whether a cosmological model makes sensible predictions. If a model implies that most observers should be random fluctuations, while we appear to live in a universe with a consistent history, galaxies, stars, planets, fossils, and breakfast, then something may be wrong with the model or with how we are reasoning about probabilities. The Boltzmann brain problem reminds us that a universe after heat death may not be simple if it lasts forever. Even stillness can become philosophically noisy when quantum fluctuations and infinite time are allowed. But for our main question, the important point is that random fluctuations are not the same as a meaningful cosmic rebirth. A new universe waking from ashes would suggest a structured beginning, a new era with low entropy conditions capable of forming stars and complexity. A random fluctuation, even an enormous one, is not necessarily a clean new beginning. It may be temporary, unstable, or causally disconnected from anything that could grow into a full cosmic history. The difference between a new universe and a strange flicker matters. There are also proposals that the far future of one universe might be mathematically related to the beginning of another. One such idea suggests that, after all matter has decayed and black holes have evaporated, the universe loses any meaningful scale. If only massless radiation remains, then the distinction between very large and very small may become less physically meaningful. Under certain mathematical transformations, the infinitely expanded future of one cosmic era could resemble the hot beginning of another. In this picture, universes follow one another not through a crunch, but through a kind of conformal transition, where the remote future of one becomes the big bang of the next. It is an elegant and unusual idea, though not confirmed. It tries to turn heat death itself into a gateway, not by gathering matter back together, but by changing how scale is understood when no massive clocks remain. This is the kind of idea that shows how creative cosmology can be. The final emptiness, usually seen as the end of all structure, becomes in this view a condition that might be reinterpreted as a new beginning. Not ashes catching fire again in the ordinary sense, but the loss of scale allowing one aeon to give way to another. Whether nature actually works this way is unknown. Evidence would be difficult, though some have searched for possible traces from a previous cosmic era in the patterns of the early universe. No widely accepted proof exists. Still, the idea is valuable because it challenges our assumption that an end must look like a wall. Sometimes, in physics, an end may look more like a change of description. The deeper problem in all these possibilities is entropy. A new universe capable of stars, chemistry, and life seems to require a low entropy beginning, or at least a condition from which useful differences can grow. Our universe began in a state that allowed structure to form. Heat death is high entropy, with usable differences spent. So any true rebirth must explain how a low entropy condition appears again. That is not a small detail, it is the central difficulty. It is one thing to say, perhaps another expansion begins. It is another to explain why that expansion starts in a special state rich enough to produce galaxies, rather than just a dull continuation of disorder. This is why scientists are careful. Rebirth is an attractive story. Humans like cycles. We see days return after nights, spring after winter, sleep after waking. We know seeds grow after fires in some forests. We are drawn to the idea that the universe might also renew itself. But the universe is not obligated to follow the emotional grammar of Earth. Cosmic rebirth must be earned by physics. It must solve the entropy problem, fit observations, and make predictions that can be compared with reality if possible. Otherwise, it remains a beautiful speculation, which is allowed, but should not be mistaken for knowledge. So could a new universe wake from the ashes? The honest answer is that it might, depending on which deeper theory of physics is true, but we do not know. It might happen through eternal inflation, with new bubble universes forming beyond our reach. It might happen through bounces if the beginning and ending of cosmic phases are connected by quantum gravity. It might happen through black holes if collapse can become expansion elsewhere. It might happen through vacuum transitions or through a mathematical bridge between the far future of one era and the birth of another. Or it might not happen at all. Heat death may be final for our universe in every practical and meaningful sense. There is no need to force comfort where the science does not give it. But there is also no need to close the door more firmly than science allows. The far future is uncertain because our knowledge is incomplete. We do not yet understand dark energy at its deepest level. We do not yet have a final theory of quantum gravity. We do not know whether protons decay. We do not know whether our vacuum is absolutely stable. We do not know whether our observable universe is all that exists or one region in a larger structure. These unknowns are not failures. They are the open windows of cosmology. Through them comes the night air, and occasionally a very strange theoretical pigeon. What we can say is that any new beginning would probably not be a rebirth for us. It would not bring back Earth, the Milky Way, or the particular history that led to this moment. If a new universe forms, it may be causally disconnected from ours. It may have different conditions. It may never inherit memories from the old universe. It may not contain the same particles, the same constants, or the same possibilities. Rebirth at the cosmic level is not reincarnation in the personal sense. It is not the universe waking up and remembering its previous dreams. It is more like a new story beginning from conditions that the old story somehow made possible, while the characters, places, and details of the old story remain gone. And perhaps that is still remarkable. The universe does not need to remember us for our moment to have been real. A future cosmos, if one exists, does not need to know about our stars for those stars to have shone. The possibility of new universes does not rescue the old one from ending, but it widens the setting in which endings occur. It suggests that the deepest reality may be more fertile than the fate of any single cosmic region. Or it may not. Either way, the question leaves us with a useful humility. We are trying to understand not just what happens to matter and radiation, but what kind of thing a universe is. Is it a one-time event, a bubble among many, a phase in a cycle, a child of a black hole, a temporary pattern in a deeper quantum structure? These are not small questions, and thankfully they are in no hurry. For now, the universe we know is still awake. Stars still burn, galaxies still shine. The cosmic microwave background still carries a message from the early fire. The future may contain stillness, decay, and perhaps a new beginning beyond anything we can observe. But we are here in the luminous interval, able to ask whether endings are truly endings. That question does not need a final answer tonight. It can rest beside us like a dim lamp. The possible futures remain spread out before the mind, some cold and quiet, some cyclic, some branching, some hidden beyond horizons, all reminding us that the edge of knowledge is not a wall, but a shoreline, and beyond it the dark water continues, carrying the next and last question gently toward us. So we arrive at the last question with the universe stretched out before us, not as a place of familiar stars and constellations, but as a complete story seen from very far away. We began with a universe still full of light, still making stars in cold clouds of gas, still glowing with galaxies and the leftover warmth of its early fire. Then we followed it forward, past the decline of starbirth, past the last small red stars, past the long age of black holes, past the slow evaporation of those black holes, and even into the uncertain fate of matter itself. We considered the stillness of heat death, the possible fading of all useful energy, and the strange chance that what looks like an ending from inside one universe may not be the end of all reality. Now the question becomes quieter and in some ways more personal. After all of this, after thinking about the end of stars and the possible end of matter, what are we supposed to do with such a thought while lying here in the dark trying to rest? It is a fair question. The end of the universe is not a practical concern in the ordinary sense. You do not need to add it to a to-do list. No one needs to wake up early tomorrow and prepare for heat death before breakfast. The timescales are so enormous that they do not fit into the rhythms of human worry. They are beyond history, beyond geology, beyond the lifetime of Earth, beyond the lifetime of the Sun, beyond the age when galaxies still look like galaxies. And yet the question still reaches us, because human beings are not only practical creatures, we are meaning-seeking creatures. We look at the sky and ask what it is. We learn that stars are born and die, and we ask what happens after the last one. We discover that black holes may evaporate, and we ask what remains. We hear that the universe may become cold and quiet, and we ask whether quiet is the same as nothing. Curiosity does not stop at useful boundaries. It wanders right up to the edge of everything, peers over, and then asks whether anyone brought a torch. There is something deeply human about that. No other species on Earth, as far as we know, lies awake wondering whether protons decay or whether a new universe can form from a vacuum fluctuation. A cat may stare into space with great seriousness, but it is probably not calculating the fate of cosmic expansion. Though with cats, one never knows. Our ability to think about the far future is one of the strangest products of the universe itself. Matter, arranged for a short time into brains, becomes capable of imagining ages when matter may no longer form brains. Stars create elements. Elements form planets. Planets develop chemistry. Chemistry produces life. Life becomes conscious. Consciousness asks what happens when consciousness is no longer possible. It is a loop of awareness so delicate and unlikely that even if the universe eventually forgets itself, for a while it remembered enough to ask. The scale of the future can feel cold at first. It can make human life seem small, and in one obvious sense, it is small. A human lifetime is brief compared with a star. A civilization is brief compared with a galaxy. Earth itself is temporary, the Sun is temporary. The Milky Way, at least as the galaxy we know, is temporary. Even black holes, those great symbols of permanence, appear to have an ending. If we measure importance only by duration, then almost everything we value seems to lose. But duration is not the only kind of importance. A song does not need to last forever to be music. A conversation does not need to echo until heat death to have mattered. A sleeping child, a garden after rain, a hand held at the right moment, a question asked honestly, a mind comforted by learning something true. These are not made worthless because they are temporary. They are the kinds of things that can only exist in a universe with time, change, and fragility. Science can describe the long future, but it does not tell us to despise the present. In fact, it often does the opposite. When we learn how special the active era of the universe is, the present becomes sharper. We live while stars still shine. We live while the cosmic background can still be detected. We live while distant galaxies are still visible. We live while matter is stable enough to form bodies, trees, oceans, books, telescopes, and blankets. We live in an era when there are strong energy differences for life to use, when sunlight pours across planets, when chemistry can build and rebuild itself, when memories can be stored in brains and written into language. The far future may be quiet, But this moment is not. This moment is full of processes. Cells repairing themselves, air moving in and out of lungs, blood carrying oxygen, neurons changing states, the planet turning, the moon pulling at oceans, the sun fusing hydrogen, galaxies moving through expanding space. You're not separate from that activity. You're one of its current forms. That is why the end of the universe does not have to be a frightening thought before sleep. It can be a way of putting the day down. The mind often clings to small concerns because small concerns are close. They have names, dates, messages, faces, bills, awkward memories, unfinished tasks, and all the little knots that gather in a normal life. The cosmic future does not solve those things directly. It will not answer an email for you, which is probably for the best, since the universe tends to reply on timescales that are not ideal for scheduling. But it can change the frame. It can remind you that your life is taking place inside something vast, old, and changing. The worry that felt enormous a moment ago may still matter, but it no longer fills the whole sky. There is room around it. The far future also teaches patience, though not the irritating kind of patience where someone tells you to relax while you're clearly holding too many bags. Cosmic patience is different. Stars take time to form. Planets take time to cool. Life takes time to evolve. Light takes time to travel. Even endings take time. The universe is not rushing toward darkness in a panic. It is unfolding through laws, transitions, and long intervals. The last stars do not vanish overnight. Black holes do not evaporate quickly. Matter, if it decays, does so at a pace so slow that ordinary imagination cannot follow it. The universe is full of gradual change. Remembering that can soften the harshness of our own expectations. Not everything needs to be resolved immediately. Not every question must be answered before morning. Some things move slowly and are still moving. And there is another lesson hidden in the idea of heat death. Complexity is temporary because it depends on usable energy. But that also means complexity is an achievement. A living body is not a violation of entropy. It is a local structure maintained by energy flow. A thought is not separate from physics. It is physics organized in a special way for a brief time. When you feel wonder, the universe is doing something rare. It is not escaping its laws. It is expressing them through an arrangement capable of awareness. We sometimes speak as though the universe is mostly empty, mostly dark, mostly indifferent, and in a broad statistical sense that is true. But it is also true that the universe has produced islands of warmth and order. It has produced stars, planets, and at least one world where matter can look up and understand that stars are made of atoms, and that atoms are made of smaller things. The fact that this will not last forever does not make it less remarkable. It may make it more remarkable. When people ask what happens after the end of the universe, they may be asking several questions at once. They may be asking what the scientific models predict. They may be asking whether anything can survive. They may be asking whether time itself continues. They may be asking whether endings are real. And sometimes, underneath those questions, there is a quieter one. If everything changes and eventually fades, can anything matter? The scientific answer cannot be the whole answer, because meaning is not a particle we can isolate, or a radiation spectrum we can measure. But science can help clear the ground. It can show that impermanence is not an exception in the universe. It is the normal condition of things. Stars are temporary, worlds are temporary, civilizations are temporary, moments are temporary. Meaning then cannot depend on being exempt from change. It must live within change. That is not a weak kind of meaning. It may be the only kind we have ever known. A meal matters because it nourishes someone, not because it remains uneaten forever. A candle matters because it gives light while it burns, not because it avoids becoming shorter. A life matters because of experience, relationship, action, memory, care, discovery, and the effects it has on other lives. The universe does not need to preserve a thing eternally for that thing to have been real. A wave rises and falls, but while it exists, it has shape, energy, and motion. We are waves of matter and time, brief but structured, temporary but not imaginary. In the farthest future, if heat death comes, there may be no one left to remember the bright era. The stars will not mourn themselves, black holes will not regret evaporating, particles will not pause to honour the galaxies from which they came. Mourning and honour belong to beings like us, in the active era. That can sound lonely, but it also gives us responsibility. If beauty is to be noticed, it is noticed now. If kindness is to be given, it is given by beings who exist while energy still flows. If knowledge is to be sought, it is sought during the window when the universe is readable. We are not waiting for the universe to tell us what matters at the end. We are part of the universe mattering now, in the ways available to conscious life. So perhaps the last question before sleep is not only what happens after the end of the universe, perhaps it is also what happens before then. What happens in this interval of light? What happens while stars still make mornings possible? What happens while there are voices, listeners, questions, and enough warmth in the room for a living body to rest? The answer is not grand in the way cosmic theories are grand, but it is closer to us. We live, we learn, we care, we look outward, we make small shelters against the dark. We tell stories so that the mind can carry more than one moment at a time. We study the universe not because study will make us permanent, but because understanding is one of the forms that temporary life can take. There is a gentle irony in using the end of everything as a path towards sleep. Sleep is not an ending in the cosmic sense. It is a daily return, a biological rhythm tied to light, darkness, memory, and repair. When you fall asleep, your body does not stop. It changes mode. The brain processes memories. Cells maintain themselves. Hormones shift. The world continues outside the window. The earth keeps turning, carrying your sleeping body under the sky. In the morning, if all goes well, you wake into the same universe, though slightly farther along its timeline. Cosmic endings are not like that. The final stillness does not wake into Tuesday. But thinking about it can make ordinary sleep feel like a gift, a small, safe surrender inside a universe that still has mornings. And there will be many mornings yet, on Earth and elsewhere, before the long future unfolds. The sun will rise tomorrow for us because we live in the present stellar age. Somewhere in the galaxy, young stars are still forming. Somewhere planets are moving through their first billion years. Somewhere old stars are cooling into white dwarfs. Somewhere black holes are quietly bending spacetime. The universe is not finished. It is not even close to finished by any human measure. We have spent this time looking far ahead, but when we return our attention to now, we find a cosmos still rich with light and motion. The end is a scientific horizon, not the weather outside tonight. If a new universe can one day arise from some deeper process, it may never know us. If no new universe arises, and our cosmos fades into stillness, it still had this. It had stars. It had chemistry. It had worlds. It had at least one species that learned to measure the age of rocks, decode starlight, detect gravitational waves, and wonder about the fate of black holes. It had music, mathematics, oceans, migrations, sleep, humour, and the unreasonable human habit of asking questions just when everyone else thought it was time to turn off the light. That is not a small legacy, even if no eternal record remains. The record exists while it exists. We are part of it. So let the final image be simple. Not the last particle drifting through infinite dark. Not the final black hole flashing away. Not a new universe bursting from some hidden quantum doorway. Those may be useful images for thought, but they are too large to hold tightly before sleep. Instead, picture the universe tonight as it truly is from our small place within it. The room around you is quiet. Your breathing is steadying. The earth is turning beneath you without needing your supervision. Above the clouds, the stars are burning, each one spending itself slowly in the dark. Beyond them, galaxies carry ancient light across space. Beyond what we can see, the future waits in forms we can model but not visit. And here, for a brief while, matter has become aware enough to rest. Wherever you're listening from, whatever time it is in your corner of the world, you're here during the bright interval. The universe has not grown quiet yet. There is still warmth, still structure, still thought, still the soft animal need for sleep. If this journey has brought you a little calm, or helped make the vastness feel less heavy, then perhaps that is enough for tonight. The last question does not need to be solved before your eyes close. It can remain open, resting gently at the edge of the mind. What happens after the end of the universe may be stillness, or transformation, or something our physics has not yet learned how to name. But what happens now is simpler. The body settles, the day loosens its grip, the thoughts that seemed sharp begin to blur. The stars continue their distant work. And for this small moment in the long life of everything, you can let the universe be large, let the future be far away, and let yourself sleep well.